atmospheric conditions over geological timescales. Additionally, active volcanism could enrich the atmosphere with gases like water vapor and carbon dioxide, fostering a dynamic environment that might support a diverse array of ecosystems. The atmospheric composition of this alien world, though currently unknown, plays a crucial role in determining its habitability. A thick atmosphere with a balanced greenhouse effect could create temperate conditions suitable for liquid water, while an excess of greenhouse gases might result in a superheated environment akin to Venus. Conversely, a thinner atmosphere could leave the surface vulnerable to harmful stellar radiation, limiting the potential for life to develop. Future telescopes equipped with advanced spectroscopic tools, like the James Webb Space Telescope, aim to analyze such atmospheres, searching for chemical signatures that might hint at habitability or even life. This second Earth also serves as a reminder of the challenges in detecting and studying distant worlds. At a distance of 1,400 light-years, direct exploration is currently impossible, but spectroscopy allows scientists to infer details about its atmosphere and surface conditions. By analyzing the light filtered through its atmosphere during transits, researchers can identify the presence of key gases like oxygen, methane, or water vapor, which are potential biosignatures. The coexistence of these gases in disequilibrium would be a strong indicator of biological processes. Scientists are particularly intrigued by the potential for water on this super-Earth. Liquid water is considered the foundation of life as we know it, and its presence would greatly enhance the likelihood of habitability. If vast oceans exist, they could regulate the planet's climate, while also serving as cradles for early life, much like Earth's ancient seas. Even if surface water is absent, subsurface oceans heated by geothermal energy could provide stable environments for microbial life, similar to the icy moons of our solar system, such as Europa and Enceladus. The elder sibling of our planet is also a key to understanding the future of planetary systems. As its host star continues to age and brighten, its habitable zone will move outward, potentially making other planets in the system more habitable. Such shifts in stellar energy output provide critical insights into the evolution of planetary climates and the long-term potential for life. Comparing the conditions on this world to younger Earth analogs could help scientists identify universal patterns in planetary evolution and the factors that determine whether a world remains habitable. The discovery of this far-off cousin highlights the importance of missions like Kepler, which revolutionized exoplanet detection by using the transit method. This technique, which involves measuring the dimming of a star's light as a planet passes in front of it, has revealed thousands of exoplanets, each contributing unique insights into the diversity of planetary systems. As next-generation telescopes and observatories come online, the ability to study planets like this in greater detail will improve, providing answers to fundamental questions about their composition, climate, and potential for life. This celestial neighbor also drives innovation in space exploration and technology. Concepts like light sails, fusion drives, and even speculative ideas like warp drives are being developed with the ultimate goal of interstellar exploration. While direct travel to this world remains a distant dream, the drive to explore such planets inspires advancements that could bring humanity closer to the stars. This exoplanet, often referred to as a super-Earth or Earth's twin, is not just a scientific marvel but also a philosophical beacon. It challenges humanity to reflect on the possibility of life beyond our planet and our place in the universe. Its discovery suggests that Earth-like planets might be common, and with them, the potential for countless forms of life scattered across the galaxy. At the same time, the vast distances between these worlds remind us of the isolation of planetary systems and the immense challenges of reaching them. The study of this Earth analog pushes the boundaries of human understanding and fosters a deeper appreciation for the fragility and uniqueness of our own world. It serves as a reminder of the incredible complexity of the cosmos and the unyielding curiosity that drives humanity to explore the unknown. As we look to the stars and uncover worlds like this, we are reminded of the endless possibilities that await us in the vast expanse of space. The potential significance of Kepler 452b, often called a super-Earth or an Earth cousin, extends far beyond its physical characteristics. It opens the door to profound scientific and existential questions. Its discovery by the Kepler Space Telescope was a landmark moment in the hunt for planets that might harbor life, and it has since fueled interest in the search for habitable worlds across the galaxy. This distant planet, orbiting a star that resembles our Sun but is older and brighter, offers scientists a model for studying what happens to planetary environments as stars evolve over billions of years. The advanced age of its host star makes it particularly fascinating. Kepler 452, a G-type star like our Sun, has already been shining for approximately 6 billion years. This means that any biosphere on the planet would have had an additional 1.5 billion years to evolve compared to life on Earth. This extended timeline raises fascinating possibilities. If life emerged there, it might have reached levels of complexity or technological sophistication far beyond anything seen on our planet. Alternatively, the planet might illustrate the fragility of biospheres, showing how environmental changes driven by stellar aging could lead to the decline or extinction of life. One of the most intriguing aspects of this exoplanet is its potential atmosphere. While direct observations remain out of reach, theoretical models suggest it may possess a thick and stable atmosphere due to its larger size and higher gravity. A dense atmosphere could insulate the surface, regulate temperature extremes, and protect against harmful radiation from space. However, its exact composition would dictate whether it supports conditions similar to Earth or veers toward the extremes of Venus. For instance, an atmosphere dominated by carbon dioxide could create a runaway greenhouse effect, turning the planet into a searing wasteland. On the other hand, a balanced mix of nitrogen, oxygen, and water vapor could sustain a temperate climate suitable for liquid water and, potentially, life. The planet's surface conditions, though speculative, are equally captivating. If it is a rocky world, as many models suggest, it might feature diverse geological landscapes shaped by tectonic and volcanic activity. The stronger gravity and thicker crust could lead to towering mountain ranges, deep ocean basins, or expansive plateaus. Tectonic activity, in particular, would play a critical role in recycling essential nutrients and stabilizing the planet's climate over geological timescales. Volcanism could replenish the atmosphere with gases like water vapor and carbon dioxide, which are crucial for maintaining warmth and potentially fostering ecosystems. This second Earth is also a prime candidate for exploring the role of liquid water in habitability. Water is essential for life as we know it, serving as a solvent for biochemical reactions and a medium for transporting nutrients. If the planet has oceans, they could regulate the climate through the absorption and redistribution of heat. These hypothetical oceans might also act as incubators for life, similar to Earth's early seas. Even if surface water is absent due to extreme conditions, the planet could harbor subsurface oceans heated by geothermal activity, akin to the environments on moons like Europa or Enceladus in our solar system. Kepler 452b's position within the habitable zone of its star adds further weight to its potential habitability. This Goldilocks zone is the region around a star where temperatures allow liquid water to exist on a planet's surface. The planet's orbital period of 385 Earth days places it firmly within this zone, but its proximity to an older, brighter star raises questions about its current climate. Receiving about 10% more stellar energy than Earth, the planet may have experienced significant warming over time. If it has mechanisms like reflective clouds or a dynamic carbon cycle, it might still maintain stable, habitable conditions. However, if these systems failed, the planet could have transitioned into a hotter, less hospitable state. The discovery of this exoplanet also emphasizes the importance of searching for biosignatures, chemical markers that indicate the presence of life. Future space missions equipped with advanced spectrographs aim to analyze the atmospheres of such distant worlds, looking for signs of oxygen, methane, ozone, or other gases that are out of equilibrium. For instance, the simultaneous presence of oxygen and methane in an atmosphere would strongly suggest biological activity, as these gases react quickly and would not coexist without being replenished by life forms. While the distance to Kepler 452b makes detecting such biosignatures extremely challenging, its study lays the groundwork for refining the techniques and technologies needed to probe exoplanetary atmospheres. Beyond its scientific allure, the discovery of this distant Earth twin has profound philosophical implications. It forces us to consider the possibility that life might not be unique to our planet and that the galaxy could be teeming with worlds harboring diverse ecosystems. It challenges our understanding of life's universality and resilience, as well as our assumptions about how civilizations might develop and survive in different environments. If advanced life exists, or once existed, on this faraway world, what could it teach us about our own future? And if the planet is barren, what lessons might it hold about the fragile balance required for life to thrive? This far-flung neighbor also serves as a powerful motivator for advancing space exploration. While it is far beyond the reach of current propulsion technologies, its discovery has inspired researchers to think creatively about how to overcome the barriers of interstellar travel. Concepts like light sails, antimatter propulsion, and even speculative ideas like warp drives are being explored as potential means of reaching distant stars. Although these technologies remain theoretical, the desire to explore planets like Kepler 452b drives innovation and expands humanity's understanding of what is possible. The role of this exoplanet in humanity's quest to understand the universe cannot be overstated. It represents a milestone in our search for habitable worlds and serves as a reminder of the vastness and diversity of the cosmos. While we may never set foot on its surface, studying its characteristics helps us refine our understanding of planetary science and habitability. It also highlights the importance of missions like the Kepler Space Telescope, which have revolutionized our ability to detect and study exoplanets. This distant super-Earth, sometimes referred to as an Earth cousin or a potential future Earth, has captured the imagination of scientists and the public alike. It stands as a testament to humanity's unyielding curiosity and desire to explore the unknown. As we continue to discover more about planets like this, we edge closer to answering one of the most profound questions of all: are we alone in the universe? Kepler 452b, often called Earth's older cousin, represents a milestone in our journey to understand the cosmos and our place within it. Its discovery raises not just scientific questions but also existential ones, forcing us to ponder the potential for life elsewhere and the future of our own planet. As we continue to delve into the mysteries of this distant world, every detail, no matter how small, adds another piece to the puzzle of understanding planetary evolution, habitability, and life itself. The advanced age of this planet's star, approximately 6 billion years, is one of its most fascinating aspects. For a system like this, the prolonged period of stellar luminosity increases the odds that the planet has undergone significant climatic and geological changes. If we consider Earth's history, where life took billions of years to evolve into complex organisms, the possibility arises that this distant super-Earth had even more time for life to emerge and adapt. However, this extended timeline also opens the door to darker possibilities, such as the complete extinction of life if environmental conditions became too harsh as the star aged and brightened. The larger size and mass of this exoplanet would fundamentally alter its physical and environmental characteristics compared to Earth. With a radius 1.5 times that of our planet and a likely mass at least 5 times greater, surface gravity would be significantly higher. This stronger gravitational pull could retain a much denser atmosphere, insulating the surface and potentially providing stable conditions for liquid water. However, the thicker atmosphere might also lead to extreme pressures, influencing the chemical composition, even the behavior of water, possibly creating supercritical states where water behaves neither as a liquid nor gas. These conditions might foster unique ecosystems unlike anything we've ever imagined. Its position in the habitable zone, often referred to as the Goldilocks zone, is central to its allure. The planet's 385-day orbit places it at a distance where stellar radiation could sustain liquid water without boiling it away or freezing it solid. However, the additional 10% energy it receives from its older and brighter star means that its climate dynamics would likely differ from Earth's. If the planet has mechanisms to reflect excess energy, such as extensive cloud cover or ice caps, it could maintain a relatively moderate climate. If not, it might face runaway warming, similar to what transformed Venus into a scorched and uninhabitable world. Speculation about the atmosphere of this alien Earth drives much of the scientific intrigue. If it contains water vapor, oxygen, or methane, it could indicate processes akin to those that sustain life on Earth. For instance, oxygen might result from photosynthetic organisms, while methane could indicate microbial activity. Alternatively, the planet might be dominated by carbon dioxide, hinting at volcanic activity or a less hospitable environment. While current technology cannot directly observe these gases from 1,400 light-years away, future telescopes equipped with advanced spectrographs might detect these chemical fingerprints, offering invaluable insights into the planet's potential habitability. The potential for water on this world remains one of its most captivating features. Liquid water is the cornerstone of life as we know it, and its presence would dramatically increase the chances of habitability. If the planet has vast oceans, these could stabilize its climate, much like Earth's oceans, by distributing heat around the globe. These hypothetical oceans might also serve as cradles for life, fostering the complex chemical reactions needed for biological activity. Even if surface water is scarce, the possibility of subsurface oceans, kept warm by geothermal activity, cannot be ruled out. Such environments, shielded from surface radiation, could provide stable conditions for microbial life to thrive. The geological history of this super-Earth is another area of intense scientific speculation. With its larger size and mass, it likely retained more internal heat than Earth, fueling prolonged tectonic and volcanic activity. Active tectonics could recycle key elements like carbon and nitrogen, maintaining a balanced atmosphere and preventing climate extremes. Volcanism could also release gases that contribute to a greenhouse effect, creating a warm and stable climate over billions of years. If such processes occurred, the planet might exhibit diverse terrains, from towering mountain ranges to expansive volcanic plains, providing a variety of habitats for potential life. This distant cousin of Earth also serves as a model for studying the effects of aging stars on planetary systems. As Kepler 452 continues to brighten with age, its habitable zone will gradually move outward. This means that while this alien Earth might currently be within the habitable zone, it may not remain there indefinitely. Understanding these changes could provide valuable insights into the long-term habitability of planets around Sun-like stars and what might happen to Earth as our Sun ages. The search for biosignatures on this world is one of the most exciting challenges for future science. Biosignatures are chemical markers, such as oxygen, methane, or ozone, that might indicate the presence of life. Detecting these signals requires advanced technologies and careful analysis, as non-biological processes can sometimes mimic biological ones. For example, methane can be produced by both microbes and geological processes, so its detection alone is not definitive proof of life. However, the simultaneous presence of oxygen and methane, especially in disequilibrium, would strongly suggest biological activity. Such discoveries would not only revolutionize our understanding of life in the universe but also raise profound questions about its diversity and prevalence. The immense distance of this Earth twin, at 1,400 light-years, makes direct exploration impossible with current propulsion technology. Yet this challenge has inspired innovative thinking about how to overcome the barriers of interstellar travel. Concepts like laser-driven light sails, fusion propulsion, and antimatter engines are being developed with the hope of one day reaching distant stars. While these technologies remain theoretical, the very idea of exploring such worlds drives technological advancement and fosters international collaboration. This far-off world, sometimes called the elder sibling of Earth, holds a mirror to our own planet's future. It reminds us that Earth, too, exists within a delicate balance, and changes in our Sun's luminosity or our planet's atmosphere could one day alter its habitability. By studying exoplanets like this, scientists gain a deeper understanding of the conditions that make a world livable and the processes that can sustain, or extinguish, life over geological timescales. Beyond its scientific implications, this distant super-Earth captures the imagination of humanity. It challenges us to think about what might exist on worlds beyond our own and whether we are alone in the universe. It sparks dreams of exploration, innovation, and discovery, reminding us of the unyielding curiosity that defines the human spirit. As we continue to uncover the secrets of this extraordinary planet, it will undoubtedly remain a symbol of the infinite possibilities that await us in the vast expanse of space. This extraordinary world, often referred to as a super-Earth or an Earth twin, continues to captivate scientists and dreamers alike. The implications of its discovery ripple across numerous scientific fields, from planetary science and astrobiology to the future of interstellar exploration. Kepler 452b serves as both a scientific beacon and a philosophical reminder of the vastness of the universe and the endless possibilities it holds. One of the most tantalizing aspects of this planet is its potential to provide insights into the longevity of habitable conditions on Earth-like worlds. With its host star being approximately 1.5 billion years older than the Sun, the planet's environment may have already undergone stages of evolution that Earth has yet to experience. This makes it a valuable analog for predicting how Earth might change as our Sun gradually brightens and ages. Over billions of years, the warming of its star likely caused significant shifts in the planet's climate, possibly transforming it from a temperate, water-rich world into a harsher environment. These insights could help scientists better understand the delicate balance that sustains life and how planetary habitability evolves over time. The potential atmospheric composition of this exoplanet is another source of intrigue. The planet's greater size and mass suggest it could retain a thicker, more stable atmosphere compared to Earth. This atmosphere might act as a protective shield, mitigating temperature extremes and providing a stable environment for chemical and biological processes. However, the balance of gases within this atmosphere is critical. A high concentration of greenhouse gases like carbon dioxide could lead to a runaway greenhouse effect, creating a hostile environment similar to Venus. Conversely, an atmosphere balanced with oxygen, nitrogen, and water vapor could sustain conditions favorable for life, potentially resembling those on Earth. Spectroscopic analysis of this distant world, using next-generation telescopes like the James Webb Space Telescope, may one day reveal these secrets. The possibility of liquid water on the planet further elevates its status as a potential haven for life. Water is not only essential for known biological processes but also plays a vital role in regulating climate. If this super-Earth has extensive oceans, they could serve as thermal reservoirs, distributing heat across the planet and moderating temperature fluctuations. These oceans might also act as cradles for life, where early biochemical reactions could give rise to simple organisms. Even if the planet lacks surface water due to the intense energy from its star, there remains the possibility of subsurface oceans. These could be heated by geothermal activity, providing stable conditions for microbial ecosystems, much like the environments found beneath the icy crusts of Europa and Enceladus. The geological processes on this faraway cousin of Earth are another area of fascination. A planet with its estimated size and mass would likely have a dynamic interior, driven by heat from radioactive decay and residual energy from its formation. This heat could fuel robust tectonic activity, creating diverse terrains and recycling critical elements like carbon and nitrogen. Active plate tectonics, if present, could stabilize the planet's climate over geological timescales by regulating atmospheric carbon dioxide levels. Volcanism, on the other hand, could enrich the atmosphere with essential gases, contributing to a greenhouse effect that supports liquid water. These processes, coupled with the planet's size, might create a wide variety of habitats, from mountain ranges and volcanic plains to deep ocean basins. The planet's location within the habitable zone, often called the Goldilocks zone, is key to its allure. This region around a star is where temperatures allow liquid water to exist, making it a prime target for the search for life. The similarity of its orbital period, 385 days, to Earth's adds to its appeal, suggesting it experiences similar seasonal and climatic cycles. However, the increased energy it receives from its brighter star raises questions about its current habitability. If the planet's surface is shielded by reflective clouds or ice, it might still maintain moderate conditions. On the other hand, if its atmosphere has failed to adapt to the increased energy, the planet could have transitioned into a state of extreme warming. The search for biosignatures on this Earth cousin remains one of the most ambitious goals of exoplanetary science. Biosignatures are chemical markers, such as oxygen, methane, or ozone, that indicate the presence of biological processes. Detecting these signatures is a monumental challenge, given the planet's distance of 1,400 light-years, but advancements in spectroscopy and telescope technology offer hope. The detection of oxygen and methane in disequilibrium, for example, would strongly suggest biological activity, as these gases react quickly and would not coexist without continuous replenishment by life forms. Even the presence of water vapor or other volatile compounds could provide crucial clues about the planet's potential to support life. This distant super-Earth also serves as a catalyst for innovation in space exploration. While it lies far beyond the reach of current propulsion technologies, its discovery has inspired bold concepts for interstellar travel. Ideas such as light sails propelled by lasers, fusion-powered spacecraft, and even speculative warp drive technologies are being explored as potential methods for reaching distant stars. While these technologies remain in their infancy, the desire to explore planets like this one drives innovation and pushes the boundaries of what is possible. The very idea of interstellar travel unites humanity in a shared vision of exploration and discovery. Philosophically, this world challenges us to reflect on our place in the universe. It forces us to confront the possibility that Earth is not unique and that countless other worlds, each with their own histories and potential biospheres, may exist across the galaxy. The notion that life might thrive, or might once have thrived, on such a distant world prompts profound questions about the prevalence and diversity of life in the cosmos. If advanced civilizations have ever arisen on this planet, what might they have achieved during the billions of years of its existence? And if it is barren, what does that teach us about the fragile conditions required for life to flourish? This remarkable discovery also emphasizes the importance of preserving the conditions that make Earth habitable. By studying distant planets like this one, scientists gain a better understanding of the factors that sustain life and the delicate balance required to maintain it. These lessons are not only valuable for understanding other worlds but also for safeguarding our own. In every way, this far-off world embodies the spirit of exploration and curiosity that drives humanity to reach beyond its limits. It reminds us that the universe is vast, mysterious, and full of potential. As we continue to study this extraordinary planet, it will remain a symbol of hope and inspiration, a testament to the boundless possibilities that await us in the stars. The allure of Kepler 452b, often nicknamed Earth's distant twin, extends beyond its scientific intrigue, serving as a symbol of the boundless potential for discovery in the cosmos. Its very existence challenges our understanding of planetary formation, habitability, and the nature of life itself. While it is located over 1,400 light-years away, the insights gained from studying this exoplanet reverberate across disciplines, pushing the frontiers of human knowledge and imagination. As one of the earliest discovered exoplanets firmly situated within its star's habitable zone, this super-Earth has become a focal point for scientists searching for worlds capable of sustaining life. Its star, a G-type main-sequence star similar to our Sun, is not only older but also more luminous. This stellar brightness likely had profound effects on the planet's climate over billions of years. Early in its history, the planet may have enjoyed conditions strikingly similar to those of early Earth, with temperate climates, abundant liquid water, and a stable atmosphere. However, as the star aged and brightened, these conditions could have changed dramatically. This raises crucial questions about how long planets in similar circumstances can remain habitable, offering a glimpse into Earth's potential future as our Sun evolves. The sheer mass of this distant world suggests an entirely different physical reality compared to Earth. With an estimated mass at least 5 times greater, its surface gravity would exert a significantly stronger pull. This enhanced gravity would likely have profound implications for its atmosphere, enabling it to retain gases that would escape from smaller planets like Mars. A denser atmosphere might provide robust protection against cosmic radiation and stellar winds, preserving conditions necessary for life. However, it could also lead to extreme pressures on the surface, potentially creating an environment radically different from what we experience on Earth. The planet's geological activity is another fascinating aspect of its potential habitability. Its large size likely ensures a molten interior, sustained by radioactive decay and the residual heat from its formation. This internal energy could drive plate tectonics, which play a critical role in recycling essential elements like carbon and maintaining a stable climate. Volcanic activity, if present, might contribute gases such as water vapor and carbon dioxide to the atmosphere, supporting a greenhouse effect that could stabilize surface temperatures. The combination of tectonic and volcanic processes might also create diverse habitats, from underwater thermal vents to mountainous regions, providing numerous opportunities for life to develop and evolve. One of the most captivating possibilities is the presence of water, whether on the surface or hidden beneath layers of rock and ice. Water is fundamental to life as we know it, and its presence would significantly enhance the planet's potential for habitability. If vast oceans exist, they could regulate the planet's climate, distributing heat evenly and preventing extreme temperature fluctuations. These oceans might also foster complex chemical reactions, providing the conditions necessary for the emergence of life. Even in the absence of surface water, the possibility of subsurface oceans heated by geothermal activity remains compelling. These hidden reservoirs could harbor microbial life in stable, energy-rich environments, much like those found beneath the icy crusts of Europa or Enceladus in our own solar system. The role of the planet's position within the Goldilocks zone cannot be overstated. This region, where temperatures allow liquid water to exist, is a key factor in determining habitability. The planet's orbital period of 385 days is remarkably similar to Earth's, suggesting comparable seasonal cycles and energy input from its star. However, the increased luminosity of its older host star means it receives approximately 10% more energy than Earth. This additional energy could result in a warmer climate, potentially driving a runaway greenhouse effect if the atmosphere contains excessive amounts of greenhouse gases like carbon dioxide. Alternatively, if the planet has mechanisms for regulating its climate, such as reflective cloud cover or polar ice caps, it might still maintain temperate conditions. The search for biosignatures on this alien world remains one of the most ambitious goals of exoplanet research. Biosignatures are specific chemical markers, such as oxygen, methane, or ozone, that indicate the presence of biological processes. For example, oxygen is highly reactive and would quickly disappear from an atmosphere unless replenished by life. Methane, too, is unstable in the presence of oxygen and would require continuous production by either biological or geological processes. The simultaneous detection of these gases, especially in disequilibrium, would be a strong indicator of life. While the immense distance to this planet makes such observations extraordinarily difficult, advancements in spectroscopic techniques offer hope for future discoveries. The potential habitability of this alien Earth has inspired the development of next-generation telescopes and observatories. Instruments like the James Webb Space Telescope, the European Space Agency's Plato mission, and the planned Extremely Large Telescope are poised to revolutionize our understanding of exoplanets. These technologies will enable scientists to analyze the atmospheres of distant worlds, searching for chemical signatures that might indicate habitability or even the presence of life. By studying the light that passes through a planet's atmosphere during transits, researchers can detect the fingerprints of water vapor, carbon dioxide, and other critical compounds, offering invaluable insights into the planet's composition and climate. The philosophical implications of this faraway world are as profound as its scientific significance. Its discovery forces us to confront fundamental questions about our place in the universe. Are we alone, or is life a common phenomenon in the galaxy? If civilizations have arisen on worlds like this one, what might they have achieved, and how might they view the cosmos? Conversely, if this planet is barren, what does that tell us about the rarity and fragility of life? These questions challenge our understanding of existence and inspire a sense of awe and curiosity that transcends scientific inquiry. This distant cousin of Earth also serves as a powerful motivator for innovation in space exploration. While the planet itself is far beyond the reach of current propulsion technologies, its discovery has sparked renewed interest in the possibility of interstellar travel. Concepts like laser-driven light sails, fusion-powered spacecraft, and antimatter propulsion are being explored as potential solutions to the challenge of reaching distant stars. Although these technologies remain speculative, the dream of exploring worlds like this one fuels scientific creativity and pushes the boundaries of what humanity can achieve. The legacy of this remarkable planet lies not just in the data it provides, but in the questions it inspires. Its discovery reminds us that the universe is vast, diverse, and full of possibilities. Each new detail we learn about this super-Earth brings us closer to understanding the conditions that sustain life and the factors that shape planetary systems. As humanity continues its journey into the cosmos, this distant world will remain a symbol of hope, curiosity, and the unrelenting drive to explore the unknown. Kepler 452b, a beacon of exploration and wonder, continues to serve as a symbol of the infinite possibilities in the cosmos. Its very existence highlights the vast diversity of planetary systems and the tantalizing potential for habitable worlds scattered throughout the galaxy. As we learn more about this exoplanet, it deepens our understanding of the delicate interplay between planetary evolution, stellar aging, and the conditions that make life possible. This super-Earth represents not just a scientific discovery but a gateway to new realms of inquiry. Its larger size and mass, coupled with its position within the habitable zone, place it among the most intriguing candidates for habitability. However, these same factors pose unique challenges. The planet's stronger gravity would create conditions markedly different from those on Earth, influencing everything from atmospheric dynamics to the potential evolution of life forms. Any hypothetical organisms on its surface would need to adapt to higher pressures and stronger gravitational forces, potentially resulting in compact, robust life forms better suited to such an environment. The increased luminosity of its host star, an aging G-type star, provides critical insights into the long-term habitability of planets orbiting Sun-like stars. As Kepler 452 brightened over billions of years, it likely had profound effects on the planet's climate and atmospheric chemistry. Early in its history, this distant cousin of Earth may have enjoyed stable, temperate conditions, with abundant liquid water and a thriving biosphere. However, as the star's energy output increased, the planet could have undergone significant warming, challenging any existing life to adapt to the changing environment. This gradual shift mirrors what Earth may experience in the distant future, offering a unique opportunity to study the effects of stellar aging on planetary habitability. The potential for water, both on the surface and beneath it, is one of the most exciting aspects of this alien world. Liquid water is essential for life as we know it, serving as a solvent for chemical reactions and a medium for biological processes. If this exoplanet has extensive oceans, they could act as heat sinks, moderating global temperatures and creating a stable environment for life. These hypothetical oceans might also foster diverse ecosystems, with nutrient-rich waters teeming with microbial life or even more complex organisms. Even in the absence of surface water, the possibility of subsurface oceans, warmed by geothermal activity, remains compelling. Such environments, shielded from stellar radiation, could provide stable habitats for life to persist over billions of years. The atmosphere of this second Earth is another key area of speculation. A thick, dense atmosphere might insulate the planet's surface, maintaining a stable climate and protecting it from harmful radiation. The composition of this atmosphere, whether dominated by greenhouse gases like carbon dioxide or balanced with nitrogen, oxygen, and water vapor, would dictate the planet's habitability. A balanced atmosphere could sustain temperate conditions, while an excess of greenhouse gases might create a superheated environment similar to Venus. Spectroscopic observations of this distant world, made possible by next-generation telescopes, could reveal its atmospheric makeup and provide critical clues about its climate and potential for life. The geological processes that shape this faraway world also hold great scientific interest. A planet of its size and mass would likely have an active interior, fueled by the heat of radioactive decay and residual energy from its formation. This internal energy could drive plate tectonics, volcanic activity, and the recycling of critical elements like carbon and nitrogen. These processes are essential for maintaining a stable climate over geological timescales and for creating diverse habitats where life could emerge and evolve. Active volcanoes might also release gases into the atmosphere, contributing to a greenhouse effect that supports liquid water and temperate conditions. The search for biosignatures on this alien cousin of Earth represents one of the most exciting frontiers in exoplanet research. Biosignatures are specific chemical markers that indicate the presence of biological processes. For example, oxygen is highly reactive and would quickly disappear from an atmosphere unless replenished by life. The presence of methane, ozone, or other compounds in disequilibrium could similarly point to biological activity. Detecting these markers requires advanced technologies and precise observations, but their discovery would revolutionize our understanding of life in the universe. Kepler 452b's immense distance, 1,400 light-years, poses significant challenges for direct exploration, but it also inspires the development of innovative technologies for studying distant worlds. Concepts like laser-driven light sails, which use focused beams of light to propel spacecraft at high speeds, are being explored as potential methods for interstellar travel. Fusion propulsion and other advanced concepts, though still theoretical, represent humanity's determination to overcome the barriers of distance and time to reach the stars. While direct exploration of this distant world may remain out of reach for generations, its discovery fuels our collective imagination and drives progress in space exploration. The philosophical implications of this exoplanet are as profound as its scientific significance. Its discovery challenges us to rethink our place in the universe and consider the possibility that life might not be unique to Earth. If life exists, or once existed, on this distant world, what might it look like? How might it have evolved under conditions so different from our own? And if the planet is barren, what lessons can we learn about the fragility of habitability and the factors that sustain life? These questions resonate deeply, inspiring awe and curiosity as we strive to understand the cosmos. Kepler 452b, often referred to as Earth's twin or the elder sibling of our planet, represents the best of humanity's scientific and exploratory spirit. It serves as a reminder of the vastness of the universe and the endless possibilities it holds. As we continue to study this extraordinary world, it will remain a symbol of hope, a testament to the unyielding curiosity that drives us to explore, and a beacon guiding us toward the stars. Each new discovery about this planet brings us closer to understanding the broader narrative of life in the cosmos, making it not just a scientific marvel, but a source of inspiration for generations to come. The story of Kepler 452b, sometimes called Earth's elder cousin, continues to inspire as it holds tantalizing clues about the potential for life and the dynamics of planetary evolution in the galaxy. This distant super-Earth symbolizes humanity's relentless curiosity, as every insight gained from its study brings us closer to understanding the fundamental processes that shape habitable worlds. Though 1,400 light-years away, the echoes of its discovery resonate across multiple disciplines, pushing the boundaries of science and imagination alike. This exoplanet's advanced age, tied to its host star's 6 billion-year lifespan, presents an extraordinary opportunity to study the long-term evolution of planetary systems. While Earth is nestled in the Sun's habitable zone today, scientists know that our star will brighten as it ages, eventually making Earth uninhabitable. Kepler 452b may already be in this later stage of habitability, providing a glimpse of the challenges a planet might face as its host star grows increasingly luminous. Such observations allow researchers to refine their models of stellar aging and planetary responses, shedding light on the delicate balance required to sustain life over billions of years. The super-Earth's size and mass continue to draw speculation about its geological and atmospheric characteristics. With a radius 1.5 times that of Earth and a likely mass 5 times greater, the planet's gravity would significantly impact its physical environment. A thicker crust and stronger gravitational pull might influence the types of landforms that develop, leading to unique geological features unlike anything seen on Earth. Mountains could be taller and steeper, while ocean basins might be deeper, potentially hosting vast underwater ecosystems. These factors would also affect atmospheric circulation, possibly driving more extreme weather patterns or stabilizing global temperatures depending on the planet's composition. Its atmosphere, though unobservable with current technology, is one of the most critical factors influencing its habitability. The dense gravity of this super-Earth likely enables it to retain a thicker atmosphere over time, even as stellar radiation gradually increases. This atmosphere might act as both a protective barrier and a thermal regulator, trapping heat to create stable surface temperatures. However, the composition of the atmosphere is key. A high concentration of greenhouse gases, like carbon dioxide, might drive a runaway greenhouse effect, heating the planet to uninhabitable levels. On the other hand, a balance of nitrogen, oxygen, and water vapor could sustain temperate climates and enable the development of life. Water is central to the intrigue surrounding this distant world. The presence of liquid water is considered a cornerstone of habitability, and the planet's position within the Goldilocks zone raises the possibility of vast oceans or lakes on its surface. If oceans exist, they could regulate the planet's climate, distributing heat from the equator to the poles and preventing extreme temperature fluctuations. These water bodies could also serve as a habitat for microbial life or more complex organisms, providing the necessary medium for biochemical processes. Even if surface water is absent, subsurface oceans heated by geothermal energy remain a possibility, offering a haven for life shielded from stellar radiation and temperature extremes. Kepler 452b's geological activity, driven by its larger mass and internal heat, might be another critical factor in its potential habitability. The planet's size suggests it could retain significant geothermal energy, fueling active plate tectonics and volcanism. Tectonic activity would help recycle essential elements like carbon and sulfur, stabilizing the planet's climate over geological timescales. Volcanism, meanwhile, could replenish the atmosphere with water vapor and greenhouse gases, maintaining warmth and supporting a dynamic environment. These processes, coupled with a stable atmosphere, could create diverse habitats capable of supporting life. The search for biosignatures, chemical markers of life, on this alien cousin of Earth represents one of the most exciting challenges in exoplanetary science. Advanced telescopes and spectroscopic instruments are being developed to detect gases like oxygen, methane, and ozone in the atmospheres of distant worlds. The presence of these gases, particularly in disequilibrium, would strongly suggest biological activity. For example, oxygen would not remain abundant in an atmosphere without being replenished by life, as it reacts quickly with other compounds. Similarly, the coexistence of methane and oxygen would indicate active biological processes, as these gases would otherwise destroy each other. Observing such markers on Kepler 452b would be a groundbreaking achievement, revolutionizing our understanding of life in the universe. The vast distance to this distant super-Earth poses a formidable challenge, but it has also inspired a surge in innovative thinking about interstellar exploration. Concepts like light sails, which use beams of light to propel spacecraft at incredible speeds, are being developed as potential methods for reaching distant stars. Fusion propulsion and antimatter engines are also under consideration, offering theoretical solutions to the immense distances involved. While these technologies remain in the realm of the future, they reflect humanity's determination to explore worlds beyond our own, driven by the desire to uncover the secrets of planets like Kepler 452b. Philosophically, this alien world forces us to confront the possibility that Earth is not unique. The idea that there could be countless planets with similar conditions across the galaxy expands our understanding of the cosmos and our place within it. If life exists, or once existed, on this distant cousin, what might it teach us about the universality of biological processes? If it is barren, what does that tell us about the delicate balance required for life to emerge? These questions resonate deeply, challenging our assumptions about the rarity of life and inspiring awe at the complexity of the universe. The discovery of this faraway twin also underscores the importance of Earth's habitability and the need to protect it. By studying worlds like this one, scientists gain valuable insights into the conditions that sustain life and the factors that could lead to its decline. These lessons are not only relevant to exoplanetary science but also critical for addressing the challenges of climate change and environmental stewardship here at home. Kepler 452b reminds us of the fragility and preciousness of our planet and the imperative to preserve it for future generations. As humanity continues its exploration of the cosmos, this Earth twin will remain a symbol of hope and curiosity. It represents the unyielding drive to push beyond our limits, to seek answers to the most profound questions, and to uncover the mysteries of the universe. Each new discovery about this extraordinary world brings us closer to understanding the broader narrative of life in the cosmos. In its quiet, distant orbit, Kepler 452b stands as a testament to the infinite possibilities that await us among the stars. Kepler 452b, often referred to as a window into Earth's future, continues to fascinate researchers and space enthusiasts alike. Its discovery not only expands our understanding of planetary systems but also serves as a profound reminder of the sheer scale and diversity of the cosmos. As we piece together the story of this distant world, every new insight adds to the broader narrative of planetary evolution, habitability, and the potential for life beyond Earth. One of the most compelling aspects of this distant cousin is its potential to mirror what Earth might one day become. As its host star, Kepler 452, has aged over the course of 6 billion years, its luminosity has increased. This gradual brightening likely caused the habitable zone to move outward, impacting the planet's climate and possibly its ability to sustain life. If the planet once had conditions similar to Earth, it may now be undergoing transitions that hint at how our own world will evolve as the sun ages and brightens in the coming billions of years. Such a connection makes Kepler 452b an invaluable natural laboratory for understanding the future of Earth-like planets. The planet's size and gravity add layers of complexity to its potential environment. With a mass likely 5 times that of Earth, the planet's surface gravity would be significantly stronger. This would affect not only the retention of atmospheric gases but also the way life, if it exists, might adapt to such conditions. Organisms on this super-Earth might evolve compact and robust structures to counteract the effects of gravity. Meanwhile, the stronger gravitational pull would likely enable the planet to maintain a thick atmosphere over billions of years, even as stellar radiation increased. This thick atmosphere could act as a shield, protecting the surface from harmful cosmic and ultraviolet radiation while regulating surface temperatures. The question of water remains central to the intrigue surrounding Kepler 452b. If surface oceans exist, they could serve as stabilizing forces for the planet's climate, absorbing heat during periods of increased solar radiation and redistributing it through atmospheric circulation. These oceans might also support thriving ecosystems, providing the medium for biochemical processes that could give rise to life. On Earth, hydrothermal vents on the ocean floor are known to host rich microbial communities, and similar environments could potentially exist on this distant world. Even if the surface lacks water, subsurface oceans heated by geothermal energy could provide stable, life-supporting environments shielded from the harsher conditions above. The geology of this elder Earth is another area of immense interest. A planet of its size and mass would likely have an active interior, driven by significant geothermal energy. Plate tectonics, if present, could play a critical role in recycling essential elements and stabilizing the climate. Volcanic activity might release gases like carbon dioxide and water vapor into the atmosphere, contributing to a greenhouse effect that maintains temperate conditions. These geological processes could also create diverse environments, ranging from towering mountains to deep valleys and expansive volcanic plains, offering a variety of niches where life might take hold. The potential atmosphere of this super-Earth is one of its most tantalizing mysteries. A thicker atmosphere could create conditions conducive to life by providing warmth, shielding the surface from radiation, and supporting a dynamic climate system. However, the specific composition of the atmosphere would determine the planet's habitability. If dominated by carbon dioxide, the planet could experience a runaway greenhouse effect, heating the surface to extreme levels. Conversely, a balance of nitrogen, oxygen, and water vapor could sustain temperate climates similar to those on Earth. Future telescopes with advanced spectroscopic capabilities, like the James Webb Space Telescope and its successors, aim to analyze the light passing through exoplanet atmospheres, potentially revealing the chemical fingerprints of life. The search for biosignatures, chemical markers that indicate the presence of life, on this distant world represents the next frontier in exoplanetary science. Biosignatures like oxygen, ozone, or methane, particularly when found in disequilibrium, would strongly suggest biological processes. For example, oxygen is a highly reactive gas that would quickly disappear from an atmosphere unless continuously replenished by life. Similarly, methane is unstable in the presence of oxygen and would require active production to persist. Detecting these gases in the atmosphere of Kepler 452b would be a groundbreaking discovery, providing the first direct evidence of life beyond Earth. The discovery of this distant world has also sparked significant interest in interstellar exploration. While Kepler 452b lies far beyond the reach of current spacecraft, its existence motivates the development of advanced propulsion technologies that could one day make interstellar travel a reality. Concepts such as laser-driven light sails, which could accelerate small probes to a significant fraction of the speed of light, are already being explored. Fusion propulsion and other speculative technologies offer additional possibilities, reflecting humanity's determination to reach beyond the confines of our solar system. Philosophically, this planet challenges us to rethink our place in the universe. Its discovery highlights the possibility that life might not be unique to Earth, but rather a common phenomenon in the galaxy. If life exists, or once existed, on Kepler 452b, what might it look like? Would it follow evolutionary patterns similar to those on Earth, or would it take entirely different forms? And if the planet is lifeless, what does that tell us about the factors that make a world habitable? These questions push us to reflect on the fragility and uniqueness of our own biosphere while igniting a sense of wonder about the cosmos. Kepler 452b also underscores the importance of preserving the habitability of Earth. By studying distant worlds, we gain a deeper appreciation for the delicate balance that sustains life and the potential consequences of disrupting it. The lessons learned from studying planets like this can inform our understanding of climate change, planetary ecosystems, and the long-term stewardship of our home world. As we look toward the future, this elder sibling of Earth will remain a focal point of scientific inquiry and exploration. It symbolizes the unrelenting drive to understand our universe and the infinite possibilities that await us among the stars. Each new discovery about Kepler 452b deepens our understanding of what it means to be a habitable world and what it might take to find, or one day visit, another Earth. It stands as a testament to the enduring curiosity and ingenuity of humanity, inspiring future generations to look to the skies and continue the quest for knowledge. Kepler 452b, often dubbed a second Earth, stands as a beacon of scientific curiosity and human ambition, continuously inviting deeper exploration of its mysteries. Its discovery not only marks a milestone in the search for habitable worlds but also highlights the profound potential for life and planetary diversity across the galaxy. As our understanding of this distant world grows, so too does our awareness of the complexities involved in finding, studying, and potentially reaching planets beyond our solar system. This distant super-Earth offers a unique perspective on the relationship between planets and their host stars. With its star being significantly older and more luminous than the Sun, Kepler 452b provides a glimpse into the long-term evolution of habitable zones. Over billions of years, the increasing brightness of its star likely transformed the planet's climate, potentially shifting it from a temperate, water-rich world to one that is hotter and more volatile. These changes mirror what scientists predict will happen to Earth as the Sun continues to age, offering valuable insights into the future of planetary habitability in our own solar system. The planet's size and mass are central to its scientific intrigue. As a super-Earth, it occupies a category of planets larger than Earth but smaller than ice giants like Neptune. Its greater mass suggests a stronger gravitational pull, which would have profound implications for its atmosphere, geology, and potential biosphere. A denser atmosphere could provide long-term stability, protecting the surface from harmful stellar radiation and maintaining conditions suitable for liquid water. However, the stronger gravity might also lead to extreme surface pressures, influencing the types of environments and ecosystems that could exist. These factors challenge our understanding of how life might adapt to conditions fundamentally different from those on Earth. Water, as always, lies at the heart of habitability. If Kepler 452b possesses surface oceans, they could regulate its climate, creating stable conditions where life might flourish. These oceans could act as reservoirs for heat, preventing extreme temperature fluctuations and fostering the chemical reactions necessary for life to arise. Even if surface water is absent due to the planet's proximity to its bright star, subsurface oceans heated by geothermal activity could provide a stable, life-supporting environment. On Earth, similar conditions are found beneath ice-covered regions and in deep-sea hydrothermal vents, where thriving ecosystems exist despite harsh surface conditions. The geological features of this super-Earth also offer a compelling avenue for study. A planet of its size and mass would likely retain significant geothermal energy, driving active plate tectonics and volcanism. These processes are essential for recycling critical elements like carbon and nitrogen, which play a key role in maintaining atmospheric stability. Volcanic activity could also release gases like carbon dioxide and water vapor into the atmosphere, supporting a greenhouse effect that stabilizes surface temperatures. These geological dynamics, coupled with potential surface and subsurface water, could create a wide variety of habitats, each with the potential to host life. The planet's position within the habitable zone of its star is another point of fascination. Often referred to as the Goldilocks zone, this region is where temperatures allow liquid water to exist on a planet's surface. Kepler 452b's 385-day orbit places it well within this zone, but its older stars' increased luminosity presents challenges. The additional energy it receives could lead to warming, potentially triggering a runaway greenhouse effect if its atmosphere contains significant amounts of carbon dioxide. Alternatively, reflective cloud cover or ice caps might help regulate its climate, maintaining temperate conditions despite the increased stellar radiation. Atmospheric composition remains a critical unknown for Kepler 452b. A thick, stable atmosphere could protect the surface from radiation, regulate temperatures, and support a dynamic climate system. However, the specific balance of gases would determine the planet's habitability. For instance, an atmosphere rich in oxygen and water vapor could indicate Earth-like conditions, while one dominated by carbon dioxide might suggest a superheated, Venus-like environment. Spectroscopic studies using advanced telescopes are expected to shed light on the planet's atmosphere, potentially revealing the presence of biosignatures, chemical markers of life. The search for biosignatures on this Earth twin represents a frontier in exoplanet science. Detecting gases like oxygen, methane, or ozone in disequilibrium would strongly suggest biological processes. For example, the coexistence of oxygen and methane, which react quickly with one another, would require continuous replenishment by life or non-biological processes. Water vapor, carbon dioxide, and other volatile compounds might also provide clues about the planet's climate and potential habitability. While the immense distance to Kepler 452b makes such observations challenging, the ongoing development of next-generation telescopes promises to bring us closer to uncovering its secrets. Kepler 452b's discovery has also reignited discussions about the future of interstellar exploration. Although it lies far beyond the reach of current propulsion technologies, its existence motivates the pursuit of advanced methods for reaching distant stars. Concepts like laser-driven light sails, which could propel small spacecraft at a fraction of the speed of light, are being actively explored. Fusion-powered engines and speculative ideas like warp drives also remain areas of intense research. While these technologies are still in their infancy, the dream of visiting or studying worlds like Kepler 452b continues to inspire innovation and drive progress. Beyond the scientific and technological implications, this distant planet challenges us to reflect on profound philosophical questions. Its discovery forces us to consider whether life is a common phenomenon in the universe or a rare occurrence unique to Earth. If life exists, or once existed, on Kepler 452b, what form might it take? How might it have adapted to the planet's unique conditions? Conversely, if the planet is barren, what does that tell us about the fragility of habitability and the factors required for life to emerge? These questions deepen our understanding of the cosmos and our place within it. Kepler 452b also serves as a powerful reminder of the importance of preserving the habitability of Earth. By studying other planets, we gain insights into the delicate balance of factors that sustain life and the consequences of disrupting that balance. These lessons are especially relevant in the face of global challenges like climate change, emphasizing the need to protect our own planet for future generations. As humanity looks to the stars, Kepler 452b will continue to stand as a symbol of hope, curiosity, and the unyielding drive to explore the unknown. Each new discovery about this extraordinary world brings us closer to answering some of the most profound questions about life, the universe, and our place within it. In its quiet, distant orbit, this elder sibling of Earth reminds us of the infinite possibilities that lie beyond the horizon, waiting to be uncovered by those brave enough to seek them. Kepler 452b, often seen as a mirror of possibility, continues to inspire humanity's imagination and scientific ambition. It stands as a silent testament to the vastness of the cosmos and the mysteries waiting to be uncovered. Every new theory or observation tied to this super-Earth sharpens our understanding of planetary formation, the prerequisites for life, and the future of habitability in a changing universe. It also fuels our collective dream of reaching distant worlds and understanding what lies beyond the familiar confines of our solar system. The aging star around which this planet orbits serves as a reminder of the cosmic timescales at play. Kepler 452, a G-type star like our Sun, has provided a relatively stable environment for over 6 billion years, offering ample time for any potential life forms on the planet to develop and evolve. If biological processes ever took root here, they would have had far longer to mature compared to Earth. This extended timeline raises intriguing possibilities. What could a biosphere look like after billions of years of uninterrupted evolution? Could intelligent life have emerged and perhaps even declined as the planet's climate changed with the star's increasing luminosity? Or might microbial life persist in specialized niches, adapting to harsher conditions as the planet warms? The size and gravity of Kepler 452b introduce profound implications for its environment and potential inhabitants. With gravity roughly twice as strong as Earth's, the physical and biological processes on this planet would likely differ significantly. Taller mountain ranges, deeper ocean basins, and more extreme weather patterns might define its surface. The higher gravity could also influence the evolution of life, favoring compact, squat organisms capable of withstanding the greater gravitational pull. If intelligent life exists or existed here, it may have developed technologies and infrastructure vastly different from our own, shaped by the unique challenges of their world. The atmospheric conditions on this super-Earth remain a tantalizing mystery. If the planet has retained a thick, stable atmosphere, it could create a dynamic environment capable of supporting liquid water and regulating temperatures. The composition of the atmosphere, however, holds the key to understanding its climate and habitability. A balance of nitrogen, oxygen, and water vapor could suggest Earth-like conditions, while an atmosphere dominated by carbon dioxide might indicate a runaway greenhouse effect. Reflective cloud cover, if present, could mitigate some of the warming caused by its aging star, stabilizing surface temperatures and extending the planet's habitable lifespan. Water, as always, is a focal point in the search for life. Kepler 452b's position within the habitable zone makes the presence of liquid water a distinct possibility. Surface oceans, if they exist, could act as vast heat reservoirs, moderating the planet's climate and supporting diverse ecosystems. These oceans might harbor complex chemical interactions, providing a foundation for life to emerge and flourish. Even if surface water has evaporated due to increased stellar radiation, subsurface oceans heated by geothermal activity could persist, offering a refuge for microbial life in stable, energy-rich environments. The geological dynamics of Kepler 452b are equally fascinating. With its larger size and mass, the planet likely retains significant geothermal energy, driving plate tectonics and volcanic activity. These processes are critical for recycling elements like carbon and sulfur, which play essential roles in maintaining a stable atmosphere. Active volcanoes could also contribute to the greenhouse effect by releasing gases like carbon dioxide and water vapor into the atmosphere, potentially supporting temperate surface conditions. The interplay between geology, atmosphere, and climate would shape the planet's surface and create varied environments where life might thrive. The search for biosignatures on this distant world is one of the most exciting and challenging endeavors in modern astronomy. Advanced telescopes like the James Webb Space Telescope and its successors are designed to analyze the light passing through exoplanetary atmospheres, searching for chemical fingerprints of life. Oxygen, methane, and ozone are among the most promising biosignatures, as their presence, especially in disequilibrium, would strongly suggest biological processes. For example, the simultaneous detection of oxygen and methane would be highly significant, as these gases would quickly react with each other in the absence of active replenishment. The detection of such markers on Kepler 452b would represent a monumental breakthrough in our understanding of life in the universe. Kepler 452b also underscores the challenges and opportunities of interstellar exploration. At 1,400 light-years away, the planet is far beyond the reach of current propulsion technologies. Yet its discovery inspires innovative ideas for reaching distant stars. Concepts like laser-driven light sails, which could accelerate small spacecraft to a significant fraction of the speed of light, are actively being developed. Fusion propulsion and other speculative technologies, while still theoretical, offer hope for one day bridging the vast distances between stars. These advancements reflect humanity's enduring determination to explore the unknown and uncover the secrets of distant worlds. Beyond its scientific significance, this distant cousin of Earth holds profound philosophical implications. It forces us to confront the question of whether we are alone in the universe. If life exists, or once existed, on Kepler 452b, what might it teach us about the resilience and adaptability of life? If it is barren, what lessons can we draw about the rarity of habitable conditions and the fragility of life-supporting environments? These questions inspire awe and humility, reminding us of the interconnectedness of all life and the unique position Earth holds in the cosmos. Kepler 452b also serves as a powerful reminder of the importance of safeguarding our own planet. By studying distant worlds, we gain valuable insights into the factors that sustain life and the consequences of disrupting those conditions. These lessons are particularly relevant as humanity grapples with challenges like climate change and environmental degradation. The distant super-Earth calls us to action, urging us to protect the delicate balance that makes our world habitable. As we look to the stars, Kepler 452b will remain a symbol of humanity's unyielding curiosity and drive to explore. Its discovery represents not just a scientific achievement but also a testament to the ingenuity and determination of those who seek to understand the universe. Each new insight about this extraordinary planet brings us closer to answering some of the most profound questions about life, the cosmos, and our place within it. In its silent orbit, Kepler 452b invites us to dream, to innovate, and to push the boundaries of what is possible, reminding us that the pursuit of knowledge knows no limits. Kepler 452b, in its quiet orbit around an ancient star, serves as a timeless reminder of the infinite possibilities within the cosmos. It challenges us to reflect on the fragility and resilience of life, the uniqueness of Earth, and the potential for countless other worlds scattered throughout the galaxy. Its discovery not only deepens our understanding of the universe but also ignites our collective imagination, inspiring humanity to dream of what lies beyond the horizon. While the distance to this super-Earth renders direct exploration impossible for now, its story is far from finished. Each technological advancement and each new observation brings us closer to uncovering its secrets. As scientists refine their models, develop powerful telescopes, and push the boundaries of space travel, Kepler 452b remains a beacon guiding us toward a future where the stars feel just a little closer. Ultimately, this distant world embodies the spirit of exploration, the relentless curiosity that has driven humanity to climb mountains, cross oceans, and now, to gaze at the heavens in search of answers. Whether Kepler 452b is a cradle of life, a barren rock, or something entirely beyond our imagination, it will forever hold a place in the narrative of human discovery. As we continue our journey into the unknown, Kepler 452b reminds us that the pursuit of knowledge is not merely about reaching destinations but about expanding our understanding of ourselves and our universe. It is a call to wonder, to innovate, and to explore, a testament to humanity's enduring quest to find its place among the stars. The TRAPPIST-1 system, a captivating jewel in the cosmos, continues to astonish astronomers and astrobiologists alike. At the heart of this system lies TRAPPIST-1e, a rocky world with the tantalizing potential to harbor life. Orbiting a dim, ultra-cool red dwarf star just 39 light-years away in the Aquarius constellation, this exoplanet represents one of the most promising candidates for studying Earth-like conditions beyond our solar system. The TRAPPIST-1 star system, first unveiled in 2017, features 7 terrestrial planets, all comparable in size to Earth. Discovered by the Transiting Planets and Planetesimals Small Telescope, TRAPPIST, and further studied using instruments like the Spitzer Space Telescope and Hubble, this planetary family orbits its star with extraordinary proximity. TRAPPIST-1e, often called the Earth analog, resides comfortably in the system's habitable zone, where temperatures may permit liquid water to pool on its surface. Unlike our Sun, TRAPPIST-1 is a red dwarf, only 9% as massive and significantly cooler. This means that planets like TRAPPIST-1e, despite their tight orbits, receive just enough stellar energy to sustain potentially life-friendly environments without the scorching effects of proximity seen in our inner solar system. One of the most compelling aspects of TRAPPIST-1e is its potential to host a stable, Earth-like atmosphere. Researchers have leveraged advanced tools like the James Webb Space Telescope, JWST, to search for biosignatures, gases like oxygen, methane, or carbon dioxide, which might hint at biological activity. Initial studies suggest that TRAPPIST-1e likely possesses a rocky composition with a density strikingly similar to Earth's, increasing the odds that it retains an atmosphere conducive to life. The planet's surface is another topic of intrigue. TRAPPIST-1e likely exhibits tidal locking, with one hemisphere perpetually facing its star while the other remains in darkness. This unique feature creates stark temperature contrasts but may also foster complex weather systems. The planet's terminator line, where day meets night, could serve as a temperate sweet spot for habitability. Water is the cornerstone of life as we know it, and TRAPPIST-1e holds promise in this regard. The habitable zone placement implies that, under the right atmospheric conditions, liquid water could exist on its surface. Spectroscopic analyses conducted with the JWST aim to detect water vapor signatures, which would dramatically enhance the planet's appeal as a life-friendly world. The possibility of subsurface oceans, similar to those on Europa or Enceladus in our own solar system, cannot be ruled out. If TRAPPIST-1e harbors underground water reservoirs, they may be shielded from stellar radiation, offering a haven for microbial life. Researchers are also investigating whether volcanic activity or hydrothermal vents could provide the necessary energy to sustain life forms. Despite its many alluring qualities, TRAPPIST-1e faces challenges common to planets orbiting red dwarf stars. Stellar flares and intense radiation bursts from TRAPPIST-1 could strip away planetary atmospheres over time. However, if TRAPPIST-1e's magnetic field is robust, it might shield the planet from these destructive forces, preserving its atmosphere and habitability. Moreover, the long lifespans of red dwarf stars offer an advantage. While our Sun has a lifespan of roughly 10 billion years, red dwarfs like TRAPPIST-1 can burn for trillions of years. This extended stability provides ample time for life to emerge and evolve, assuming other conditions are met. The exploration of TRAPPIST-1e and its sister planets represents a cornerstone of modern exoplanetary science. Missions like the JWST and future observatories, such as the Extremely Large Telescope, ELT, are poised to unlock the secrets of this extraordinary system. By analyzing starlight as it passes through TRAPPIST-1E's atmosphere, scientists hope to identify chemical fingerprints that could point to biological activity. In addition to remote observations, visionary proposals for interstellar probes could one day bring humanity closer to TRAPPIST-1E. Concepts like Breakthrough Starshot aim to propel spacecraft to nearby star systems within a few decades. While such missions remain in their infancy, they highlight the growing ambition to directly study worlds like TRAPPIST-1E. The quest to understand whether we are alone in the universe hinges on planets like TRAPPIST-1E. As an Earth-like world in a relatively nearby system, it provides an unparalleled opportunity to test hypotheses about life's universality. If signs of life are detected, it would revolutionize our understanding of biology and the cosmos. Conversely, if TRAPPIST-1E proves lifeless despite its favorable conditions, it may underscore the uniqueness of Earth's biosphere. Such findings would carry profound philosophical and scientific implications, reshaping our perspective on the fragility and rarity of life. This enigmatic exoplanet, often referred to as the Second Earth, stands as a beacon of possibility in the vastness of space. Orbiting its dim star within the habitable zone, the world, sometimes called the twilight planet due to its tidally locked nature, beckons scientists with its tantalizing promise of alien environments. The study of this celestial neighbor has revealed a planet that defies simple categorization, blending characteristics of terrestrial worlds with the unique challenges posed by its extreme proximity to a red dwarf. The shadowed half of this distant globe, bathed in perpetual night, may hold vast reserves of frozen water, locked away beneath icy crusts. Meanwhile, the sunlit hemisphere endures the unyielding radiation of its faint but volatile parent star. Yet, it is the terminator region, a thin band where light and darkness meet, that has captured the imagination of astrobiologists. Here, conditions may be just right for the formation of liquid water, a critical ingredient for the emergence of life. This so-called golden crescent represents a fascinating test case for planetary habitability beyond Earth. The star system, hosting this extraordinary sphere of rock and possibility, challenges our understanding of planetary formation and survival. In contrast to our solar system, where gas giants like Jupiter act as shields against incoming debris, the worlds orbiting this red dwarf lack such massive protectors. And yet, the exoplanet of twilight appears remarkably stable, defying expectations of chaotic bombardment. This stability raises questions about the early history of its formation and the role of interstellar forces in shaping its destiny. Further study of this stellar sibling has revealed its remarkable density, suggesting a planet rich in heavy metals and silicates. Such a composition hints at a geologically active surface, potentially marked by volcanic activity or tectonic shifts. If so, these processes could play a pivotal role in recycling carbon dioxide and other greenhouse gases, creating a self-regulating climate system akin to Earth's. Alternatively, the lack of plate tectonics might result in a static environment, where ancient surface features endure for billions of years. Exploration of this exo-Earth has sparked debates about the role of magnetospheres in sustaining habitability. On our home planet, Earth's magnetic field shields us from harmful solar winds and cosmic radiation, preserving the atmosphere and enabling life to thrive. Scientists hypothesize that this alien world may possess a similar magnetic shield, generated by a molten iron core. If true, it would bolster hopes for the long-term stability of its climate and atmospheric composition. Without such a shield, however, the relentless stellar flares from its red dwarf star could strip away any protective gases, rendering the eternal dusk planet a barren, airless wasteland. The possibility of microbial life on this rocky orb ignites fierce curiosity. Could extremophiles, microorganisms capable of thriving in extreme conditions find a foothold in the planet's more temperate regions? If so, they might exist in forms entirely alien to us, adapting to a world of stark contrasts and perpetual extremes. The discovery of even the simplest life forms here would profoundly alter our understanding of biology and the adaptability of living systems. Astronomers continue to refine their models of the Earth analog, using state-of-the-art telescopes to analyze its atmospheric composition. With the advent of instruments like the James Webb Space Telescope, scientists hope to detect biosignatures, subtle chemical imprints of life. The presence of gases such as oxygen, methane, or ozone in its atmosphere would be a groundbreaking discovery, pointing to the possibility of biological activity. Conversely, a barren atmosphere dominated by carbon dioxide or nitrogen could imply a lifeless world, reminding us of the fragility of life in the cosmos. This alien cousin of Earth also serves as a proving ground for interstellar exploration. While current technology limits us to remote observations, visionary projects like Breakthrough Starshot hint at a future where humanity might send robotic emissaries to nearby star systems. Tiny spacecraft propelled by powerful lasers could reach this distant world within decades, transmitting high-resolution data back to Earth. Such missions would mark the dawn of interstellar exploration, transforming the distant neighbor from a point of light in the night sky to a well-documented world. The cultural implications of the shadowed twin extend beyond science. Its discovery has inspired artists, writers, and dreamers to reimagine humanity's place in the universe. Depictions of its rugged landscapes, illuminated by the eerie glow of its red dwarf star, evoke a sense of wonder and longing. Could this distant planet serve as a refuge for future generations? Or is it a reminder of the uniqueness of Earth, a fragile oasis in an otherwise inhospitable cosmos? The mysteries of this stellar counterpart remain vast, and each new observation adds a piece to the puzzle. Researchers are particularly intrigued by the possibility of organic molecules forming on its surface or in its atmosphere. Such compounds, the building blocks of life, could provide crucial insights into prebiotic chemistry and the conditions necessary for life to emerge. If the pale wanderer proves hospitable to even the simplest organisms, it would redefine the boundaries of habitability and expand our understanding of life's potential in the universe. As technology advances, the study of this exosibling continues to evolve. Missions planned for the coming decades will employ advanced spectrometers, capable of analyzing the light reflected and absorbed by its surface. These observations will help determine the composition of its soil, the presence of minerals, and even the likelihood of liquid water. With each new discovery, the rocky enigma becomes less of a distant dream and more of a tangible reality, drawing us closer to answering the age-old question, are we alone? The cosmic twin of Earth continues to captivate scientists with its intricate dance around its dim star. Orbiting at a distance that perfectly balances energy and temperature, this exoplanet, often described as the Crimson Haven, embodies the delicate equilibrium necessary for life. Its close orbit around its red dwarf sun exposes it to a slow, rhythmic stellar cycle that profoundly impacts its climate and atmospheric dynamics. The perpetual day side of this tidal orb basks in the steady but subdued glow of its parent star, creating a stark contrast to the frigid night side. The boundary between these extremes, the twilight zone, could act as a crucible for complex atmospheric circulation. Winds might carry heat from the illuminated hemisphere to the frozen regions, creating conditions for water to exist in liquid form at the planet's surface or even beneath its crust. Advanced climate modeling has revealed fascinating possibilities: polar ice caps extending into the night side, massive cloud formations on the day side, and constant storms in the transition zones. This eternal twilight planet poses questions that reach beyond habitability into the realms of planetary evolution. The tidal locking it experiences is not unique. Many exoplanets close to their stars share this characteristic. Yet, TRAPPIST-1e, or the dusklit world, stands apart for its ability to potentially sustain life despite this constraint. The energy balance between the hemispheres could be moderated by atmospheric composition, with greenhouse gases like carbon dioxide or methane acting as insulators. If these gases are present in just the right proportions, the planet could maintain a stable climate over millions of years. In recent studies, astronomers have focused on the possibility of a dense, oxygen-rich atmosphere on this starlight sibling. While oxygen is often associated with biological processes, it could also result from abiotic mechanisms, such as the photodissociation of water molecules under intense stellar radiation. The existence of oxygen without accompanying methane or other biosignatures would complicate the search for life, challenging scientists to distinguish between chemical processes that mimic biological activity and those that genuinely signal life's presence. The planetary surface of this cosmic mystery is equally intriguing. If volcanic activity is ongoing, it could contribute to the replenishment of atmospheric gases while creating geothermal pockets of habitability. Hydrothermal vents, similar to those found in Earth's oceans, could provide energy sources for microbial ecosystems. These vent systems, shielded from the harsh radiation of the star, might host unique life forms that thrive in extreme environments. The very thought of alien microbes surviving under such conditions fuels the search for similar systems on other rocky worlds across the galaxy. The shadowed Earth, as some researchers call it, also offers an unparalleled opportunity to study the long-term effects of stellar radiation on planetary atmospheres. Red dwarfs, while long-lived, are notorious for their flaring activity. During these solar events, bursts of charged particles could erode a planet's atmosphere over time. Yet, TRAPPIST-1e appears to defy this trend, possibly due to a strong magnetic field generated by a liquid metallic core. This protective barrier could act as a shield, preserving the planet's habitability even in the face of constant stellar bombardment. For scientists, the alien mirror serves as a reminder of how interconnected planetary systems are. The interplay between its surface, atmosphere, and magnetic field mirrors the dynamics observed on Earth, albeit under vastly different conditions. This makes the extraterrestrial twin an ideal testbed for developing and refining models of planetary evolution, habitability, and climate science. Each observation adds a new layer of complexity to our understanding, challenging existing theories and inspiring innovative approaches. The future of research into this habitable paradox lies in the hands of next-generation observatories. The James Webb Space Telescope has already begun unlocking the secrets of its atmosphere, but even more powerful instruments, such as the upcoming LUVOIR, Large UV/Optical/IR Surveyor, promise to take the search for life to unprecedented levels. These telescopes will analyze the starlight passing through the exoplanet's atmosphere during transits, identifying chemical signatures that could point to biological activity. With each new dataset, the reddish pearl transforms from an abstract concept into a tangible world rich with scientific potential. The allure of this distant sibling extends beyond the scientific community. For philosophers, its existence forces humanity to grapple with existential questions about our place in the universe. If the Crimson Echo harbors life, it would mean that the processes leading to biology are not unique to Earth but are a natural outcome of planetary evolution under the right conditions. Conversely, if the planet is barren despite its promising characteristics, it might underscore the rarity and fragility of life as we know it. Explorers and engineers dream of the day when humanity might send robotic emissaries, or even crewed missions, to this stellar cousin. The development of advanced propulsion systems, capable of reaching nearby star systems within a human lifetime, remains a long-term goal. Concepts like fusion-powered spacecraft or laser sails could turn the dream of visiting this rocky enigma into reality. Until then, scientists must rely on remote sensing and theoretical models to decode its mysteries. This twilight orb stands as a beacon of hope and wonder in the vastness of space. Each new discovery brings humanity closer to understanding the conditions necessary for life, not just on TRAPPIST, 1e but throughout the cosmos. The study of this remarkable exoplanet serves as a bridge between science and imagination, inspiring future generations to look up at the night sky and dream of worlds yet unseen. This distant wonder, often dubbed the alien Eden, continues to redefine humanity's understanding of what it means to be habitable. Orbiting its ancient red dwarf star with such precision, the exoplanet dances in a gravitational harmony that defies the chaotic beginnings of its system. While TRAPPIST, 1e and its sister planets exist in extreme proximity to their Sun, the stability of their orbits over billions of years suggests that these worlds may have weathered the violent youth of their star, an achievement that lends further credence to the possibility of their survival as bastions of habitability. Scientists hypothesize that the planet's slow rotation, locked into tidal equilibrium, creates dynamic and turbulent atmospheric conditions. The ever-present heat on its day side may generate rising currents of air that travel toward the cold night side, cooling and condensing into massive, sprawling cloud systems. These clouds, in turn, reflect some of the incoming radiation from the red dwarf star, preventing runaway heating. Meanwhile, the frigid night side might act as a heat sink, fostering a bizarre, planet-wide exchange of energy that may sustain a globally balanced climate. The twilight frontier, as some researchers call it, is where life could flourish. This narrow, crescent-shaped region is bathed in soft, eternal dusk, with temperatures potentially hovering near Earth-like levels. Here, liquid water could exist on the surface, forming rivers, lakes, or even shallow seas. If this ribbon of twilight hosts an atmosphere thick enough to distribute warmth evenly, it might serve as an ecological oasis, teeming with microbial life forms that thrive in the delicate balance between light and dark. The geological activity of this shadowed gem remains one of the most compelling areas of research. Recent models suggest that internal heating, caused by tidal interactions with neighboring planets, could drive volcanic eruptions or even tectonic movement. Such activity would play a crucial role in maintaining the planet's atmosphere, replenishing it with vital gases while creating diverse habitats for potential life. Volcanism might also release water vapor, which, if it condenses into rain, could carve intricate landscapes of valleys and deltas, painting the surface with geological features that mirror Earth's dynamic history. As this exoplanetary sibling continues to be studied, the question of its magnetic field has become a focal point. A robust magnetic field would not only shield the planet from harmful radiation but also preserve its atmosphere against the powerful stellar winds of its red dwarf host. Without such a protective field, the planet's surface could be exposed to intense bursts of radiation during stellar flares, dramatically reducing its chances of sustaining life. Yet, even in this scenario, life might adapt by retreating underground or beneath protective layers of ice. The cosmic mirror holds a particular fascination for astrobiologists, who view it as a laboratory for testing theories about the universality of life. If the planet contains liquid water and the right chemical building blocks, life could have emerged independently, following paths this alien sanctuary, often referred to as the stellar twin, continues to captivate the scientific imagination. Orbiting its faint red star in a delicate gravitational balance, this remarkable world stands as a testament to the possibilities of life beyond our solar system. The Crimson Voyager, with its potential for hosting Earth-like conditions, challenges our understanding of planetary resilience and adaptability in extreme environments. The exocousin of Earth, locked in eternal rotation with one side facing perpetual light and the other eternal darkness, creates a unique dynamic of contrasts. Its day side, bathed in the soft red glow of its star, could be a land of scorching heat and towering clouds. The night side, frozen and silent, might be home to ice sheets or subsurface water reservoirs. Between these extremes lies the habitable band, a narrow twilight region where temperatures and conditions could align perfectly for the presence of liquid water, a prerequisite for life as we know it. The rocky wanderer, much like Earth, shows evidence of being composed largely of silicate materials and heavy elements. These properties suggest that it could harbor a solid surface, one potentially marked by a diverse landscape of plains, mountains, and perhaps ancient volcanic remnants. Scientists speculate that geothermal activity beneath the crust of this stellar sibling could create energy sources similar to Earth's hydrothermal vents, which are known to support thriving ecosystems deep in our oceans. One of the most intriguing possibilities for the shadowed orb is its atmosphere. Preliminary studies suggest the potential for a thick layer of gases that could act as a buffer against the star's radiation. If such an atmosphere exists, it might contain water vapor, carbon dioxide, and other compounds that not only sustain a stable climate but also provide essential ingredients for life. The presence of biosignatures, such as oxygen or methane, would transform the extraterrestrial Eden from a scientific curiosity into a revolutionary discovery. The twilight gem is not without its challenges. Its proximity to a red dwarf star subjects it to frequent stellar flares, which could strip away its atmosphere if unprotected. However, the existence of a magnetic field could mitigate these effects, shielding the celestial neighbor from harmful solar winds and maintaining its atmospheric integrity. This protective feature, if confirmed, would greatly enhance the planet's potential to host life, making it one of the most promising candidates in the search for habitable worlds. The dusklit enigma has also reignited discussions about interstellar exploration. Advanced telescopes like the James Webb Space Telescope are already unlocking new details about its atmospheric composition, but the dream of visiting this distant world remains alive. Concepts such as laser-propelled probes or fusion-powered spacecraft aim to bring humanity closer to the cosmic frontier, allowing us to directly study its surface and perhaps even sample its environment for signs of life. The pale Voyager is more than a distant dot of light in the sky, it represents the hopes and dreams of a species yearning to understand its place in the cosmos. Whether it is teeming with microbial ecosystems or a barren rock, the discoveries awaiting on this stellar kin will undoubtedly reshape our perspective on life's potential across the galaxy. This crimson refuge, orbiting its faint, ancient star, remains one of the most captivating enigmas of modern astronomy. Often called the exoplanetary sibling, it represents an extraordinary opportunity to explore the boundaries of planetary habitability. Nestled within its host star's habitable zone, the eternal twilight sphere offers a tantalizing glimpse into what might be a second home for life in the universe. The distant cousin of Earth exhibits a range of extraordinary features. Its tightly locked orbit creates a permanent divide between the searing day side and the frigid night side, forming a stark dichotomy across its surface. The transition zone between these extremes, often referred to as the life belt, may hold the key to understanding how life could adapt to such unique conditions. Here, temperatures are believed to hover at levels conducive to liquid water, the fundamental ingredient for life as we know it. The celestial wanderer has inspired countless theories about its atmospheric composition. Researchers hypothesize that this reddish sibling might host a thick layer of gases that moderates the temperature contrasts between its hemispheres. This atmosphere could act as a natural thermal blanket, circulating heat and creating a relatively stable environment in the twilight regions. Advanced spectroscopic studies are already underway to detect key atmospheric components such as water vapor, carbon dioxide, and oxygen, each of which could provide vital clues about the planet's habitability. The star-bound neighbor has also raised intriguing possibilities about its hydrological systems. If liquid water exists, it may form narrow rivers or shallow oceans along the planet's terminator line. Alternatively, water might be locked away as ice on the night side, periodically released through geothermal activity or subsurface heating. This shadowed oasis could serve as a breeding ground for extremophile-like organisms, adapted to thrive in conditions far harsher than those on Earth. Geological activity on the alien sibling is another avenue of intense exploration. Internal heating from tidal interactions with its neighboring planets in the TRAPPIST-1 system might drive volcanism and tectonic activity, creating a dynamic and ever-changing surface. These processes could replenish atmospheric gases and maintain long-term climate stability, critical for sustaining life. Furthermore, volcanic regions on this exotwin might host geothermal hotspots, fostering the kinds of ecosystems seen around Earth's hydrothermal vents, places where life thrives in complete isolation from sunlight. The tidally locked mystery also challenges scientists with the unique effects of its host star's red dwarf nature. These stars are known for their volatility, emitting powerful stellar flares that could erode a planet's atmosphere over time. Yet the Crimson Enigma appears to have defied this fate, likely due to its potential magnetic field. If this shield exists, it would be a vital factor in protecting the planet's atmosphere and preserving the conditions necessary for life. The dusklit pearl also represents a critical milestone for interstellar exploration. Observations of this world are paving the way for more advanced missions and instruments capable of probing its secrets in unprecedented detail. Future telescopes, such as the Extremely Large Telescope, ELT, and LUVOIR, aim to unlock even more insights into its composition, climate, and potential biosignatures. Meanwhile, visionary projects like Breakthrough Starshot dream of one day sending probes to the stellar cousin, capturing images and data from its surface within a human lifetime. The twilight orb, while still shrouded in mystery, serves as a reminder of the vast possibilities that lie beyond our solar system. Its discovery has reignited humanity's fascination with the cosmos, inspiring a new generation of explorers, scientists, and dreamers to imagine what life might look like on a world so similar yet so alien to our own. If this far-off Earth analog harbors life, it could provide answers to one of the greatest questions of all: are we alone in the universe? Even if the shadowed world proves barren, its study will teach us invaluable lessons about planetary evolution, climate dynamics, and the resilience of worlds orbiting volatile red dwarf stars. Each observation and model refines our understanding, bringing us closer to uncovering the truths hidden within the light of its distant star. The exoplanetary marvel challenges not just our scientific knowledge but also our philosophical perspectives. If it hosts life, it will reveal that biology is not unique to Earth but an intrinsic part of the universe. If it does not, it will remind us of the rarity and preciousness of our fragile blue world. Either way, the alien mirror has become an irreplaceable part of humanity's search for meaning among the stars. The crimson reflection, as some call it, is not merely an object of study, it has become a symbol of the unyielding human drive to understand the cosmos. TRAPPIST-1e, this stellar anomaly, exists as a puzzle piece in the broader tapestry of exoplanetary science, and every observation draws us closer to unraveling its secrets. Its allure lies not only in its potential to host life but in the profound questions it raises about the diversity of planetary systems and their capacity to nurture biology. The Twilight Voyager, locked in a gravitational embrace with its dim parent star, may hold answers about the adaptability of life under conditions vastly different from those on Earth. While the harsh radiation from its volatile red dwarf might seem hostile to life, some researchers argue that such conditions could drive evolution in unexpected ways. Lifeforms, if they exist on this distant echo of Earth, might have developed biochemical pathways to shield themselves from ultraviolet radiation or utilize the dim, reddish light for energy in ways we have yet to imagine. Atmospheric studies of the celestial sibling have revealed intriguing possibilities. If clouds of reflective particles exist on its day side, they could scatter incoming stellar radiation, preventing the planet from overheating. Conversely, a thicker atmosphere on the night side could act as insulation, trapping heat and maintaining a stable temperature gradient. This balance, if present, might create microclimates where complex ecosystems could thrive. The Terminator line, a perpetual band of twilight, represents the most likely candidate for such regions, a place where liquid water could pool and nutrients might circulate. Beyond its physical characteristics, the exo-Earth also offers an unparalleled opportunity to refine our methods for detecting life on distant worlds. Current efforts to analyze its atmosphere using the James Webb Space Telescope have focused on identifying specific molecules like oxygen, ozone, methane, and water vapor. The detection of these gases in the right proportions would strongly suggest biological processes. However, even the absence of such biosignatures could be valuable, pushing scientists to reevaluate what habitable truly means in the context of alien worlds. The reddish twin also serves as a natural experiment in planetary geology. Its rocky composition, combined with the intense gravitational interactions of its neighboring planets, suggests a dynamic interior. These tidal forces may generate enough internal heat to sustain volcanic activity, which could in turn support a cycling of elements between the surface and the atmosphere. Such activity, crucial for maintaining habitability over long timescales, might also create striking geological features, towering volcanoes, expansive lava plains, or deep fissures carved by tectonic shifts. The tidally bound sphere is not alone in its system, and the interplay between it and its neighboring planets offers valuable insights into multiplanetary systems. The TRAPPIST-1 system, with its 7 tightly packed worlds, is a rare opportunity to study how planetary environments evolve in close proximity to one another. The gravitational tug-of-war among these planets creates orbital resonances that stabilize their orbits, a phenomenon that might also influence their climates and potential habitability. This symphony of worlds is a cosmic dance that has persisted for billions of years, a testament to the delicate balances that nature can achieve. As humanity's technological capabilities grow, so too does the ambition to explore the alien sanctuary in greater detail. Future telescopes, both space-based and ground-based, will provide unprecedented resolution, allowing scientists to map surface features, track atmospheric changes, and perhaps even detect signs of vegetation or other large-scale biological processes. Missions like LUVOIR or HABEX could one day capture direct images of this cosmic counterpart, revealing it as more than just a point of light, a fully realized world with its own landscapes and weather systems. The twilight orb is also a source of inspiration for interstellar exploration. Concepts for reaching nearby star systems, such as Breakthrough Starshot's laser-driven probes, are already in development. These microspacecraft, capable of traveling at a significant fraction of the speed of light, could reach the TRAPPIST-1 system within a few decades, providing humanity with its first close-up view of an exoplanetary system. Such missions, though still in their infancy, highlight the growing convergence of science and engineering in the quest to explore the stars. The cultural impact of the stellar twin cannot be overstated. Its discovery has sparked a renaissance of creativity, inspiring art, literature, and philosophy that explore the implications of finding another Earth-like world. For some, the dusk-lit marvel represents hope, a vision of humanity's future among the stars. For others, it serves as a humbling reminder of Earth's uniqueness and the fragility of life in an often hostile universe. The study of this distant neighbor has profound implications for our understanding of life's potential in the cosmos. If life is found on this crimson refuge, it will confirm that biology is not a cosmic anomaly but a natural outcome of the universe's processes. If no signs of life are detected, it will sharpen our focus on the conditions that make Earth so uniquely suited for life. In either case, the exo-Earth stands as a symbol of humanity's relentless curiosity and determination to seek answers to the most profound questions. The exploration of this cosmic enigma is far from over. As each new instrument and mission brings us closer to unraveling its mysteries, the alien cousin will continue to inspire awe, challenge assumptions, and expand the boundaries of human knowledge. It is not merely a planet, it is a gateway to understanding our place in the universe and the possibilities that lie beyond. The stellar echo reminds us that the cosmos is vast, filled with worlds waiting to be explored, each one holding the potential to transform our understanding of existence itself. The crimson outlier, still shrouded in mystery, remains a focal point of scientific intrigue and speculation. Every detail we uncover about this remarkable world strengthens its position as a prime candidate for hosting life. Its placement within the habitable zone of its dim red star, a region often referred to as the Goldilocks zone, is only the beginning of the story. The stellar parallel offers far more than just favorable temperatures. It provides a glimpse into how life might emerge and evolve under entirely different cosmic circumstances. The eternal twilight sphere, with its tidally locked orbit, poses unique challenges for habitability. Unlike Earth, where the rotation creates dynamic day-night cycles, this alien world experiences an unchanging dichotomy. The day side, constantly bathed in the faint red glow of its star, might develop thick, heat-reflecting cloud layers to moderate surface temperatures. The night side, in perpetual darkness, could accumulate vast ice sheets, creating a frozen realm that contrasts starkly with the scorching heat of the day. Between these extremes, the life band, the narrow zone of perpetual dusk, offers a promising sanctuary where temperatures may remain mild enough to sustain liquid water. The possibility of water, either on the surface or locked within subsurface reservoirs, is central to the planet's allure. If liquid water exists, it could flow through the twilight zone in narrow rivers or pool into shallow lakes, creating environments rich in the potential for microbial life. The reddish twin may also harbor vast oceans beneath a thick ice crust on its dark side, similar to Europa or Enceladus in our solar system. Such subsurface oceans, warmed by geothermal activity, could provide a stable and long-lasting refuge for life, protected from the harsh radiation of its volatile red dwarf star. Astrobiologists studying the exo-Earth are particularly interested in its atmospheric composition. If the atmosphere contains greenhouse gases like carbon dioxide, methane, or even water vapor, it could trap heat efficiently, smoothing out the extreme temperature differences across the planet. Additionally, the presence of oxygen, though not necessarily a direct indicator of life, would suggest intriguing chemical processes at work. Future observations using advanced telescopes aim to probe deeper into these possibilities, searching for the subtle chemical fingerprints that might reveal whether this alien haven harbors life. The shadowed cousin also raises questions about planetary geology. Its density suggests a rocky composition, with a core rich in heavy metals and a crust capable of sustaining tectonic activity. Volcanism on the planet's surface could play a key role in recycling essential elements and releasing gases into the atmosphere, a process that might sustain a stable climate over millions of years. If hydrothermal vents exist beneath its surface, they could provide localized energy sources, fostering unique ecosystems similar to those found in Earth's deep oceans. The dusklet anomaly is not just an isolated object of fascination, it is part of a larger family of 7 planets in the TRAPPIST-1 system. These worlds, all tightly packed around their star, interact gravitationally in a delicate orbital resonance. This planetary symphony not only stabilizes their orbits but may also influence their climates and geological activity. The interactions among these worlds offer a rare opportunity to study the dynamics of compact planetary systems, shedding light on how such configurations evolve and persist over billions of years. One of the most compelling aspects of the stellar mirror is the potential impact of its parent star on its habitability. Red dwarfs, though long-lived, are known for their volatile behavior, emitting powerful flares that could strip away planetary atmospheres over time. However, the Crimson Sanctuary appears to defy this threat, potentially protected by a magnetic field that shields it from stellar radiation. If this is the case, it would mark a significant milestone in our understanding of how planets in such extreme environments can sustain life-friendly conditions. The tidal enigma has also become a testbed for cutting-edge technologies designed to explore distant worlds. Instruments like the James Webb Space Telescope are already providing unprecedented insights into its atmosphere, while future observatories, such as the Habitable Worlds Observatory, promise even greater discoveries. These tools are capable of detecting faint signals that could point to the presence of life, such as variations in atmospheric composition over time or even seasonal changes indicative of biological processes. The exosibling also fuels humanity's aspirations for interstellar exploration. Projects like Breakthrough Starshot envision sending tiny, high-speed probes to nearby star systems, including the TRAPPIST-1 system, to capture close-up images and data. Such missions, while decades away, represent the next great leap in humanity's quest to reach out into the cosmos. The Twilight Voyager stands as a symbol of what might be achievable, a distant goal that inspires engineers, scientists, and dreamers alike. Philosophically, the alien echo forces us to confront profound questions about our place in the universe. If life exists on this distant world, it would confirm that the processes leading to biology are not unique to Earth but a natural outcome of the cosmos. Such a discovery would reshape not only science but also humanity's sense of identity, proving that we are part of a larger, interconnected web of life spread across the galaxy. On the other hand, if the shadowed wonder proves barren, it would highlight the extraordinary rarity of life, underscoring the importance of preserving our fragile planet. The exploration of this crimson frontier is far from over. Each new observation peels back another layer of mystery, revealing a world that is at once familiar and alien. Whether it ultimately proves to be a cradle of life or a barren rock, the stellar cousin will forever remain a testament to humanity's insatiable curiosity and our enduring desire to understand the universe. This cosmic sibling, with its quiet orbit around a faint, ancient star, reminds us that even in the vast emptiness of space, there are places where life might yet bloom, waiting to be discovered. The reddish sanctuary, a beacon of scientific hope, continues to drive humanity's greatest questions about life and the universe. As scientists push the boundaries of technology and theory, the mysteries of this exo-Earth become clearer, yet simultaneously deeper. This alien world, orbiting quietly within its compact planetary system, acts as a natural laboratory for exploring everything from planetary geology to astrobiology to interstellar dynamics. The dusklit enigma is no longer just a point of light in the sky, it is a gateway to understanding life's potential across the cosmos. The tidal marvel, locked in gravitational stasis with one side eternally basking in light and the other forever cast in shadow, likely harbors an extraordinary range of environments. The terminator zone, where day meets night, remains the prime focus of habitability studies. This narrow band of twilight could harbor mild temperatures, liquid water, and even active weather systems. Winds from the day side may carry heat and moisture into the cooler regions, creating a cycle of precipitation and evaporation that sustains complex ecosystems, if life exists. However, the Crimson Twin does not make survival easy. The red dwarf star it orbits emits frequent solar flares, bursts of radiation that could wreak havoc on the planet's atmosphere. But there is evidence that this stellar echo might have a natural defense, a magnetic field. Generated by a molten core deep within its interior, this field could act as a shield, protecting its atmosphere from being stripped away and allowing it to sustain a stable climate over billions of years. Such a magnetic field would also open the door to possibilities for life on the surface, as it could block harmful cosmic rays while allowing essential light and heat to reach the planet. The shadowed oasis is not just a scientific curiosity, it is also a place of profound geological interest. Its density and composition suggest a rocky world similar to Earth, yet unique in its formation and evolution. Gravitational interactions with its neighboring planets in the TRAPPIST-1 system generate tidal heating, which may drive volcanic activity beneath its surface. These volcanic processes could release gases like carbon dioxide, replenishing the atmosphere and creating localized hotspots where life might flourish. If tectonic activity exists, it could further diversify the planet's surface, forming mountains, valleys, and deep ocean basins that could act as reservoirs for liquid water. The exosibling also challenges scientists to rethink their assumptions about habitability. While Earth-like conditions are often seen as the gold standard, the twilight refuge may demonstrate that life can arise and thrive under entirely different circumstances. In its dim, reddish environment, life forms might rely on alternative biochemical processes, perhaps utilizing the faint infrared light from its star as an energy source. Microbial life, if present, could be adapted to extreme radiation, high levels of carbon dioxide, or even long periods of environmental stability punctuated by bursts of activity during stellar flares. One of the most exciting aspects of the alien haven is its potential to host water in multiple forms. While liquid water on the surface remains the holy grail of astrobiology, the possibility of vast underground oceans is equally intriguing. Subsurface water could remain liquid due to geothermal heating, creating a stable, long-term habitat for life. If this cosmic cradle hosts hydrothermal vents, it might mirror the conditions thought to have given rise to life on Earth, offering a glimpse into how biology could begin elsewhere in the universe. The reddish enigma is also a technological proving ground. Instruments like the James Webb Space Telescope are already revolutionizing our ability to study distant worlds, providing detailed analyses of their atmospheres and surface conditions. Spectroscopic observations of this stellar twin have begun to reveal its atmospheric structure, with the hope of detecting biosignatures such as oxygen, methane, or even ozone. Future missions, like the LUVOIR or HABEX telescopes, will be capable of directly imaging the planet, potentially capturing the first clear view of an Earth-like world beyond our solar system. The Twilight Voyager inspires not only scientists but also engineers and futurists. Concepts for interstellar travel, such as laser-driven light sails or fusion-powered spacecraft, are being developed with planets like this in mind. A probe sent to the TRAPPIST-1 system could provide humanity with its first close-up data on an exoplanetary system, revolutionizing our understanding of the universe. Such missions, though decades or even centuries away, represent the next frontier of exploration, and the Crimson Sibling serves as a shining beacon for what might one day be achievable. Culturally, the distant cousin has sparked a renaissance in art, literature, and philosophy. Its discovery has inspired countless works of fiction, imagining what life might look like on a tidally locked world, where the sun never rises or sets. Philosophers have pondered the implications of finding life, or not finding it, on such a world. Would it prove that life is common, or would it remind us of how uniquely precious Earth is? Either way, the alien mirror forces humanity to reflect on its place in the cosmos, encouraging a broader perspective on the fragility and resilience of life. The exotwin, whether teeming with microbial life or barren and rocky, offers profound lessons about the nature of existence. If life is found on this stellar echo, it would suggest that biology is a universal phenomenon, emerging wherever conditions allow. Conversely, if the planet is lifeless despite its promising characteristics, it would underscore the rarity of Earth and the delicate balance required to sustain life. Ultimately, the Crimson Refuge represents humanity's enduring quest to explore, understand, and connect with the universe. Each new discovery brings us closer to answering the age-old question, are we alone? The dusk-lit marvel, orbiting its faint star in a quiet corner of the galaxy, reminds us that even in the vast emptiness of space, there are worlds waiting to be uncovered, worlds that may one day redefine what it means to be human. The Crimson Cradle, endlessly orbiting its faint red star, symbolizes humanity's most profound questions about the cosmos. With every passing year, this stellar counterpart grows less mysterious yet increasingly fascinating. As more data trickles in from advanced telescopes and missions, this twilight enigma becomes a mosaic of possibilities, a world that offers both tantalizing clues and infinite questions about the nature of life and planetary evolution. The alien beacon, forever caught in a gravitational lock with its host star, has long been the subject of climate modeling and speculation. Unlike Earth, where global weather systems are driven by the rotation of the planet, this dusk-lit sphere presents a more static yet equally complex challenge. Scientists believe that winds on the planet may move heat and moisture from its sunlit side to the dark hemisphere, creating immense cyclonic systems and atmospheric jets that encircle the twilight zone. This dynamic, known as atmospheric redistribution, could make the golden crescent of habitability wider than initially believed, providing an even greater chance for liquid water and life to thrive. What truly sets the shadowed sibling apart is its position within the TRAPPIST-1 system, a compact arrangement of 7 Earth-sized planets. Each of these worlds orbits its ultra-cool red dwarf star closer than Mercury does to the Sun, yet their unique gravitational resonance stabilizes the system over billions of years. This resonance also contributes to the tidal forces acting on the reddish anomaly, generating internal heat that might fuel volcanic activity or subsurface oceans. The delicate gravitational dance among these planets paints a picture of a system in harmony, each world influencing the others in ways that scientists are only beginning to understand. On the surface of the exocousin, the conditions might be far stranger than anything found on Earth. Imagine a landscape where the day side glows under a dim, eternal red light, its ground cracked and baked by the stars' constant gaze. Meanwhile, the night side would stretch into infinite darkness, a frozen wasteland where temperatures could plummet to hundreds of degrees below zero. Yet, along the terminator line, where day and night meet, there might be a zone of relative tranquility, a place of perpetual dawn or dusk, where temperatures hover around the melting point of water. Here, life might find its foothold, thriving in pools of liquid water or beneath protective layers of soil. If life exists on the Crimson Sphere, it might look nothing like what we see on Earth. Under the dim red light of its star, photosynthetic organisms, if they exist, would need to adapt to the infrared spectrum, possibly appearing black or dark gray to maximize energy absorption. Alternatively, life could exist underground, shielded from radiation and thriving near geothermal vents or within mineral-rich water reservoirs. Microbial life, similar to extremophiles on Earth, could be perfectly adapted to these harsh and alien conditions, surviving in environments that would be lethal to most terrestrial organisms. The stellar neighbor is also a treasure trove for planetary chemistry. Its atmosphere, if it exists, holds the key to understanding its potential for life. Scientists are searching for biosignatures, gases like oxygen, methane, or nitrous oxide, that would indicate biological processes. However, even the absence of such gases could reveal crucial information about its history, geology, and interactions with its parent star. The twilight enigma is not just a candidate for life but a window into the diversity of planetary atmospheres, helping us refine our search for habitable worlds across the galaxy. The tidal wonder poses a fascinating conundrum about water. While liquid water on its surface would be the most direct indicator of habitability, the possibility of subsurface oceans cannot be ignored. On Earth, similar oceans beneath the icy crusts of Europa and Enceladus teem with the chemical ingredients necessary for life. The exo-Earth might harbor vast reservoirs of water beneath its rocky surface, kept liquid by tidal and geothermal heating. These hidden oceans, if they exist, could serve as cradles for alien ecosystems, protected from the harsh radiation of its red dwarf star. From a technological standpoint, the reddish mirror represents an extraordinary challenge. Observing a planet so distant and faint requires instruments of unparalleled precision. The James Webb Space Telescope has already begun to reveal the first glimpses of its atmosphere, but the next generation of observatories promises even more. Missions like the Extremely Large Telescope, ELT, and the Habitable Worlds Observatory will bring humanity closer to answering the ultimate question: is this crimson world a home for life? Philosophically, the alien twin forces us to confront our assumptions about what it means to be alive and what constitutes a habitable planet. If this world, with its extreme conditions and faint sunlight, can sustain life, it would redefine our understanding of biology and resilience. Conversely, if it is barren despite its favorable characteristics, it might suggest that life is far rarer than we currently believe. Either way, the shadowed pearl serves as a mirror for humanity, reflecting both our hopes and our limitations in the search for meaning in the universe. The exosibling is more than just a scientific target, it is a symbol of exploration and ambition. Its discovery has already reshaped our understanding of planetary systems, proving that Earth-like worlds can exist in a wide variety of environments. As humanity continues its quest to study the Crimson Beacon, we are reminded of the vast potential of the cosmos, the endless possibilities waiting just beyond our reach. This twilight sanctuary, perched on the edge of possibility, represents the frontier of human knowledge. Whether it harbors life or stands as a monument to cosmic isolation, the stellar echo will forever remain a testament to humanity's unyielding desire to explore, to question, and to dream. The Crimson Bastion, as it has come to be known among researchers, occupies a unique place in our collective imagination. Orbiting in the tranquil glow of its ancient red dwarf star, this alien ember offers a vision of what could be, a world teetering on the edge of habitability, full of tantalizing potential. With its delicate balance of extremes, searing heat on one side, freezing cold on the other, it symbolizes resilience in the face of cosmic adversity. Yet it also serves as a mirror, reflecting our deepest questions about life, survival, and the fragility of existence. The Twilight Sanctuary is part of a planetary system so densely packed that it challenges conventional wisdom about how planets form and evolve. The TRAPPIST-1 system itself is an anomaly, 7 Earth-sized worlds, tightly clustered around a star so faint and small that it barely qualifies as a star by traditional standards. These planets, including the dusklit Wonder, are locked in a complex orbital resonance, a celestial dance that ensures their long-term stability. This arrangement defies the chaos typically associated with young planetary systems and raises questions about how such a finely tuned system could emerge. For the tidally frozen sibling, this resonance is not just a stabilizing force but also a source of energy. The gravitational pull of its neighboring planets creates tidal stresses that heat its interior, much like Jupiter's moon Io. This internal furnace could drive volcanic activity on a scale unimaginable on Earth. These volcanoes might spew gases into the atmosphere, replenishing it with carbon dioxide, water vapor, and other essential molecules, sustaining a dynamic climate for billions of years. In this way, the exo-Earth might transform what appears to be a static, barren world into a planet teeming with geological, and perhaps biological, activity. The shadowed twin also provides a rare opportunity to study the interplay between a planet's atmosphere and its host star. Red dwarfs like TRAPPIST-1 are notorious for their flaring activity, emitting bursts of radiation that could strip away a planet's atmosphere over time. Yet, the Crimson Sphere seems to have defied this fate, potentially thanks to a strong magnetic field. If confirmed, this protective field would suggest that even planets orbiting volatile stars can retain their atmospheres and remain habitable, a finding that could dramatically expand the number of worlds considered capable of supporting life. In the eternal twilight zone, where the day side transitions into night, conditions may be just right for life to emerge. Here, temperatures are mild enough to allow liquid water to pool on the surface, while the constant dim light from the star might sustain basic photosynthesis. The chemical interactions in this region could create a complex prebiotic soup, setting the stage for the first self-replicating molecules. If life exists on this alien refuge, it might resemble Earth's extremophiles, organisms that thrive in environments once thought uninhabitable. From radiation-resistant microbes to chemical-eating bacteria, the possibilities for alien life are as varied as the conditions on this cosmic haven. The reddish cradle also inspires speculation about its surface. What would it be like to stand on this alien world? On the day side, one might see a dim, crimson sky dominated by the faint disk of the star, casting long, eerie shadows. The terrain could be rugged and rocky, punctuated by rivers of molten lava or vast plains of hardened basalt. On the night side, the darkness would be absolute, broken only by the faint glow of auroras caused by charged particles interacting with the planet's magnetic field. And along the terminator, where light and dark meet, the view might be otherworldly, a sky that fades from deep black to a dusky red, over landscapes softened by perpetual twilight. The exocompanion is more than just a geological marvel. It is also a testbed for humanity's growing technological prowess. Instruments like the James Webb Space Telescope are already probing its atmosphere for signs of life, searching for gases that could reveal biological activity. These efforts are pushing the boundaries of what is scientifically possible, requiring astronomers to distinguish between natural processes and potential biosignatures. For example, oxygen in the atmosphere might result from water molecules broken apart by stellar radiation rather than photosynthesis. Such findings force researchers to reconsider what signs of life might look like on worlds vastly different from Earth. The Twilight Gem is also shaping the future of space exploration. Concepts for reaching nearby star systems, such as laser-driven probes, are being designed with planets like this in mind. These tiny spacecraft, traveling at a fraction of the speed of light, could reach the TRAPPIST-1 system in a few decades, sending back invaluable data about the Crimson Haven. Such missions represent humanity's first steps toward interstellar exploration, turning what was once science fiction into tangible goals. Philosophically, the stellar twin is a source of endless fascination. Its existence challenges us to think beyond Earth-centric definitions of life and habitability. If life exists on this dusk-lit sphere, it would force us to confront the idea that biology might be a universal phenomenon, emerging wherever the conditions allow. On the other hand, if it is barren despite its favorable conditions, it would underscore the rarity and preciousness of our own planet, a fragile oasis in a vast and uncaring universe. As humanity continues to study the alien ember, its mysteries become part of our shared story. It is not just a scientific object but a symbol of what we can achieve when curiosity and ambition drive us forward. Whether it is a cradle of life or a barren rock, the reddish sanctuary reminds us of the endless possibilities that lie beyond the boundaries of our solar system. It is a testament to the resilience of worlds, the creativity of science, and the unyielding desire to explore the unknown. The Crimson Frontier, perched in the quiet depths of the TRAPPIST-1 system, continues to capture the imagination of scientists, dreamers, and visionaries alike. This alien threshold is more than a distant planet, it is a symbol of discovery, a testament to the vastness of the universe and the potential for life beyond Earth. As humanity gazes at this dusk-lit sanctuary, it becomes a canvas for understanding how life might arise, evolve, and persist under conditions unlike anything we have known. The stellar sibling, locked in its gravitational embrace with its dim, ancient star, is both a riddle and a revelation. Its perpetual day and night sides create a world of extremes, searing heat and frigid cold separated by the tenuous balance of the twilight zone. Along this eternal dusk belt, where light and darkness meet, lies the greatest hope for habitability. This strip of mild temperatures, stretching across the planet's surface, might harbor liquid water, the cornerstone of life. Here, under the dim red glow of its star, could exist ecosystems unlike anything humanity has ever encountered. The exocompanion challenges our assumptions about what life needs to thrive. The star it orbits, though faint and cool compared to the Sun, emits powerful bursts of energy in the form of stellar flares. These flares, while potentially harmful, might also serve as a catalyst for prebiotic chemistry in the planet's atmosphere, driving the formation of complex organic molecules. If life exists on this twilight refuge, it may have adapted to these bursts of radiation, developing biochemistries that use the energy in novel ways. Such life forms might thrive in subterranean habitats or within protective layers of water, shielded from the harsh environment above. The surface of the Crimson Marvel might tell a story of resilience. Its rocky crust, shaped by billions of years of geological activity, could bear the scars of past impacts or the evidence of ongoing volcanism. Tectonic forces, driven by tidal heating, might have created towering mountain ranges, vast lava plains, or even deep fissures where geothermal activity provides a constant source of heat and nutrients. These geothermal hotspots could serve as havens for life, much like hydrothermal vents in Earth's oceans. The potential for such environments makes the reddish oasis a prime candidate for exploration and study. Beneath the surface of the tidal wonder, there may be hidden worlds of water and warmth. Subsurface oceans, heated by the planet's core, could remain liquid for billions of years, creating stable environments where life could flourish. These oceans, shielded from the radiation of the red dwarf star, might host ecosystems teeming with microbial life. If the exo-Earth harbors such hidden reservoirs, it would open new pathways for understanding how life might survive in the most unexpected places. The dusk-lit sphere also raises profound questions about atmospheric chemistry. Its atmosphere, if it exists, could be a delicate balance of gases shaped by volcanic activity, stellar radiation, and potential biological processes. Scientists are searching for biosignatures, gases like oxygen, methane, and ozone, that could signal the presence of life. However, even the absence of these gases would not mean the planet is lifeless. It could simply suggest that life there operates in ways unfamiliar to us. The Crimson Cradle forces us to expand our definitions of habitability and reconsider what life might look like on distant worlds. The Shadowed Cousin has also become a proving ground for cutting-edge technologies. Telescopes like the James Webb Space Telescope are pushing the limits of what can be observed from such vast distances, providing insights into the planet's atmospheric composition, temperature, and even surface properties. Future observatories, equipped with even more advanced instruments, will allow scientists to map the surface of the stellar neighbor, detect weather patterns, and search for the faint glimmers of light that might indicate liquid water or reflective ice. The alien ember is more than a scientific curiosity, it is a philosophical challenge. If life exists there, it would suggest that the processes leading to biology are universal, occurring wherever conditions allow. Such a discovery would transform our understanding of the universe, proving that Earth is not unique but part of a vast network of life-bearing worlds. Conversely, if the exotwin proves barren, it would underscore the rarity and preciousness of life on Earth, reminding us of the need to protect our fragile planet. The cultural impact of the reddish beacon cannot be overstated. Its discovery has inspired countless works of art, literature, and music, each exploring what it means for humanity to share the cosmos with other worlds. It has sparked debates about exploration, ethics, and our responsibility as stewards of both Earth and the universe. For many, the stellar echo represents hope, a reminder that the universe is vast and full of possibilities, waiting for us to reach out and discover them. The exosibling also fuels dreams of interstellar travel. Concepts like laser-driven light sails, fusion-powered spacecraft, and even wormhole travel are being developed with worlds like this in mind. One day, humanity may send probes or even crewed missions to this twilight jewel, turning speculation into reality. Such missions would mark the beginning of a new era in exploration, one where the boundaries of our solar system no longer constrain us. The Crimson Sanctuary, whether it harbors life or stands as a barren rock, is a testament to humanity's curiosity and determination. It is a reminder that the universe is vast, filled with worlds yet to be explored, each one holding the potential to reshape our understanding of existence. As scientists continue to study this cosmic mirror, they bring us closer to answering the age-old question: are we alone in the universe? The twilight enigma, forever circling its dim red star, is not merely a scientific subject but a vessel for humanity's greatest ambitions and deepest inquiries. It serves as a bridge between the known and the unknown, a point of convergence for science, philosophy, and the boundless potential of human imagination. Each new discovery about this crimson mystery propels us closer to understanding not only its nature but also the fundamental workings of life itself. The alien cradle, nestled in the delicate warmth of its star's habitable zone, is a reminder of the diversity of planetary systems. Unlike Earth, which orbits a stable and luminous sun, this stellar sibling exists under the flickering gaze of an ancient red dwarf. These stars are the most common type in the universe, accounting for over 70% of all stars in the Milky Way. If the reddish orb proves to be habitable or even inhabited, it would imply that life may be far more common than previously imagined, thriving around stars long overlooked in the search for extraterrestrial worlds. One of the most fascinating aspects of the exotwin is its potential adaptability to the unique challenges posed by its star. Red dwarfs emit most of their energy in the infrared spectrum, meaning that any life on the dusk-lit sphere would need to evolve mechanisms to harness this faint, red-hued light. Photosynthetic organisms, if they exist, might have pigments optimized to absorb infrared radiation, giving them a deep black or dark red appearance. These alien ecosystems, thriving under a perpetually dim sky, would transform our understanding of biology and its adaptability. The shadowed cousin also offers an opportunity to explore the role of water in shaping planetary habitability. While Earth is a water world, with over 70% of its surface covered by oceans, the Crimson Frontier might have a very different distribution of liquid water. On its perpetually frozen night side, vast ice caps could extend across the landscape, preserving water in solid form for eons. On the day side, any liquid water might exist in small, isolated pockets, heated by geothermal activity or concentrated sunlight near the equator. The twilight zone, however, offers the greatest promise, a region where water could exist in liquid form, flowing in rivers or pooling in shallow seas. These twilight seas could serve as cradles for life, rich with nutrients carried by weather patterns and geological processes. Beneath the surface of the tidal jewel, the possibility of subsurface oceans sparks endless speculation. If such oceans exist, they would be insulated from the harsh conditions above, maintained by the internal heat generated by tidal forces. These hidden seas could host ecosystems similar to those found in Earth's deep oceans, where hydrothermal vents support life entirely independent of sunlight. The reddish twin might harbor its own versions of these ecosystems, teeming with microbial life forms uniquely adapted to their alien environment. The exocompanion also challenges us to think about the long-term evolution of planets. Red dwarfs, unlike larger stars, burn their fuel at an incredibly slow rate, giving them lifespans that stretch into the trillions of years. This means that the Crimson Haven has had, and will continue to have, billions of years to evolve. If life exists there, it could be incredibly ancient, potentially predating life on Earth. Such longevity would allow for evolutionary paths and adaptations far beyond what we can currently imagine, offering a glimpse into life's potential over cosmic timescales. From a technological perspective, the stellar neighbor is pushing the boundaries of what humanity can achieve. Instruments like the James Webb Space Telescope have revolutionized our ability to study distant worlds, providing detailed data about the atmospheric composition and surface conditions of the twilight marvel. Upcoming missions, such as the Habitable Worlds Observatory, promise even greater insights, with the potential to detect weather patterns, volcanic activity, and even the chemical signatures of biological processes. These observations will not only reveal the secrets of this crimson anomaly but also refine our search for habitable worlds across the galaxy. The reddish sanctuary also serves as a proving ground for interstellar exploration. Concepts like Breakthrough Starshot, a project aimed at sending tiny, high-speed probes to nearby star systems, are being developed with worlds like this in mind. If successful, these probes could provide humanity with its first close-up images and data from the TRAPPIST-1 system, turning speculation about the alien ember into concrete knowledge. Such missions, while still in their infancy, represent humanity's first steps toward becoming an interstellar species. The dusk-lit orb also holds profound philosophical implications. Its very existence forces us to reconsider what it means to be alive and what defines a habitable world. If life is found there, it would prove that biology is not a cosmic anomaly but a natural consequence of planetary evolution. Such a discovery would forever alter our understanding of the universe and our place within it. On the other hand, If the shadowed world is barren despite its promising conditions, it would underscore the rarity and fragility of life, highlighting the importance of preserving and cherishing our own planet. Culturally, the stellar echo has already left an indelible mark. Its discovery has inspired countless works of art, literature, and music, each exploring the possibilities of life on an alien world. It has sparked debates about ethics, exploration, and our responsibilities as stewards of both Earth and the universe. For many, the exosibling represents hope, a reminder that the universe is vast and full of potential, waiting to be discovered. Ultimately, the Crimson Mystery is more than a distant planet, it is a reflection of humanity's enduring curiosity and ambition. As we continue to study this cosmic threshold, we inch closer to answering the most profound question of all: are we alone? Whether it proves to be a cradle of life or a silent, rocky world, the alien sanctuary will forever remain a symbol of humanity's unyielding desire to explore, to understand, and to dream. The Crimson Enigma, as it quietly traverses its eternal orbit around a dim red star, is more than a world, it is a beacon of possibility. This twilight cradle, locked in a delicate balance of light and shadow, continues to fuel the curiosity of humanity. The intricate interplay of forces shaping this distant planet, tidal locking, gravitational resonance, and stellar radiation, makes it a living experiment in understanding the diversity of worlds across the universe. With every passing day, our scientific tools and ambitions bring us closer to uncovering its secrets. The dusklit sanctuary stands as a stark contrast to Earth, yet it bears many parallels. Its rocky composition, size, and placement within the habitable zone make it one of the most Earth-like exoplanets ever discovered. However, its environment is far more extreme. The day side, permanently illuminated by the dim, reddish light of its star, could resemble a barren desert world, its surface scorched by heat. The night side, eternally locked in darkness, might be a frozen wasteland, its terrain coated in thick ice. But between these extremes lies the eternal twilight belt, a region of perpetual dawn and dusk where conditions might be just right for life. In this narrow band of habitability, the potential for liquid water transforms the alien frontier from an abstract concept into a tangible possibility. If water flows or pools along the Terminator line, it would open the door to ecosystems adapted to this unique environment. Here, life might take root in shallow seas or geothermal springs, thriving in conditions far removed from the cycles of sunlight and seasons that define life on Earth. The shadowed realm could host microbial ecosystems uniquely evolved to extract energy from chemical gradients, volcanic heat, or even the faint infrared glow of its star. The stellar kin is also a geological wonder. Its density suggests a core of heavy metals, much like Earth, surrounded by layers of silicate rock and possibly a thin atmosphere. Tidal heating, caused by the gravitational pull of neighboring planets, might create enough internal energy to fuel active volcanoes. These volcanoes, if present, could shape the surface of the Crimson Sibling, spewing gases into the atmosphere and driving cycles of renewal that maintain a dynamic planet. The interplay between these processes, volcanism, atmospheric chemistry, and gravitational interactions, could sustain conditions favorable for life over billions of years. The exotwin also offers unique insights into the potential longevity of habitable environments. Red dwarf stars like TRAPPIST 1 burn their fuel incredibly slowly, with lifespans that stretch into the trillions of years. This means the Crimson Refuge has had, and will continue to have, vast stretches of time to evolve. If life has emerged there, it could be ancient, potentially predating life on Earth. Such longevity raises fascinating questions about the nature of evolution on long timescales. Would life stagnate, or would it develop into forms and complexities beyond our comprehension? One of the most intriguing aspects of the alien ember is its atmosphere, or the possibility thereof. Scientists believe that if this planet retains a significant atmosphere, it must have mechanisms to protect it from the volatile flares of its red dwarf star. A magnetic field, generated by a molten core, could shield the reddish mirror from stellar radiation, preserving its atmospheric integrity. This magnetic shield, if confirmed, would make the planet an even stronger candidate for habitability. Spectroscopic studies aim to detect the chemical composition of its atmosphere, searching for signs of carbon dioxide, methane, or oxygen, gases that might indicate volcanic activity, chemical cycles, or even life. The crimson outlier also serves as a focal point for humanity's aspirations in interstellar exploration. The TRAPPIST-1 system, located just 39 light-years away, is tantalizingly close in cosmic terms. Breakthroughs in propulsion technology, such as laser-driven light sails or antimatter engines, could one day allow us to send probes to this twilight marvel. These robotic explorers could capture high-resolution images of its surface, analyze its atmosphere, and even search for chemical traces of life. The possibility of reaching this stellar sibling within a human lifetime has transformed it from a distant curiosity into a realistic goal for the future. Culturally, the dusklit orb has sparked a wave of artistic and philosophical exploration. Writers imagine civilizations thriving in the twilight zone, adapting to the perpetual contrast of light and dark. Artists depict surreal landscapes bathed in crimson light, with alien skies stretching over jagged mountains or reflective seas. Philosophers debate the implications of finding, or not finding, life on this world. Would it confirm that we are not alone, or would it remind us of Earth's singularity and fragility? Either outcome would profoundly shape our understanding of existence. The Exocompanion also pushes the boundaries of our scientific tools. The James Webb Space Telescope is already providing the most detailed look yet at its atmosphere, searching for biosignatures and weather patterns. Future instruments, like the Habitable Worlds Observatory, will take this exploration further, offering direct imaging capabilities that could reveal surface features and climate dynamics. These technologies not only deepen our understanding of the stellar echo but also prepare us for the study of countless other worlds yet to be discovered. The reddish beacon continues to inspire humanity to dream bigger. It reminds us that the universe is vast, filled with worlds waiting to be explored, each with its own unique story. Whether it harbors life or remains a silent, rocky outpost, the Crimson Sanctuary challenges us to push the limits of what we know and to embrace the infinite possibilities of what we have yet to discover. The Crimson Marvel, quietly orbiting its faint red star, has become a symbol of humanity's relentless pursuit of knowledge. This twilight jewel, poised on the edge of habitability, is more than a distant planet, it is a profound opportunity to uncover the mechanisms that shape worlds and, perhaps, life itself. As scientific instruments grow ever more powerful, the secrets of this alien wonder begin to unravel, revealing a world that is both familiar and deeply alien. The stellar counterpart has already taught us much about the diversity of planetary systems. The TRAPPIST-1 system, compact and harmonious, challenges traditional models of planet formation and evolution. 7 Earth-sized worlds, including this reddish oasis, orbit their ultra-cool red dwarf star in a tight, synchronized rhythm. This resonance not only stabilizes their orbits but also generates tidal forces that shape their internal structures and geological activity. For the tidally locked orb, this gravitational interplay could be the key to sustaining a dynamic interior, fueling volcanism and potentially creating conditions for habitability. On the surface of this exosibling, the contrasts are stark. The day side, perpetually illuminated by the dim, reddish glow of its star, might be a barren landscape scorched by heat, with vast plains of cracked rock or even molten lava. The night side, shrouded in eternal darkness, could be a frozen expanse where ice stretches endlessly across the terrain. But the terminator zone, the narrow band of perpetual twilight where the two extremes meet, offers the greatest promise. Here, temperatures may remain stable enough for liquid water to exist, forming lakes, rivers, or even shallow seas. This twilight sanctuary could serve as the foundation for ecosystems uniquely adapted to the planet's eternal balance of light and dark. The Crimson Refuge is also a laboratory for studying atmospheric processes. If it possesses a significant atmosphere, it would need to withstand the challenges posed by its red dwarf star's frequent flares. These bursts of stellar radiation could strip away unprotected atmospheres, leaving the planet barren. However, the stellar echo might have developed defenses, perhaps a magnetic field generated by a molten core, or an atmosphere dense enough to absorb and redistribute the energy. Scientists are eager to understand how such a planet might maintain equilibrium under such harsh conditions, as this knowledge could reshape our understanding of habitability. Beneath the surface of the dusk-lit sphere, the possibility of subsurface oceans is particularly exciting. Tidal heating, driven by the gravitational pull of neighboring planets, could generate enough energy to keep water liquid beneath an icy crust. These hidden oceans, protected from the radiation of the star, might be teeming with life. On Earth, similar environments, such as the oceans beneath the ice of Europa or the hydrothermal vents in the deep sea, are rich with biodiversity. If the shadowed cradle hosts such environments, it would suggest that life could thrive in conditions far removed from the warmth of a sunlit surface. The exotwin also challenges us to expand our definitions of life and its potential adaptations. Any organisms on this world would need to survive under dim red light, extreme temperature gradients, and fluctuating radiation levels. Life on the reddish gem might rely on entirely different biochemistries, perhaps using chemical energy from geothermal vents or ultraviolet radiation from stellar flares. Photosynthetic organisms, if they exist, could evolve pigments optimized to absorb the infrared light of the star, giving them a dark, alien appearance. Such discoveries would redefine our understanding of biology and its resilience. The Crimson Anomaly has also become a focal point for technological advancement. The James Webb Space Telescope has already begun analyzing its atmosphere, searching for biosignatures like oxygen, methane, and water vapor. These molecules, if found in the right proportions, could indicate biological processes. Upcoming telescopes like the Extremely Large Telescope, ELT, and the Habitable Worlds Observatory will take these efforts further, enabling direct imaging of the stellar neighbor and revealing details about its surface, climate, and potential habitability. Interstellar exploration dreams are increasingly tied to the Twilight Beacon. Concepts like Breakthrough Starshot envision sending microprobes to the TRAPPIST-1 system, traveling at a fraction of the speed of light. These tiny, laser-powered spacecraft could reach the system within a few decades, capturing high-resolution images of the exocompanion and its neighbors. Such missions, though ambitious, represent humanity's first steps toward exploring worlds beyond our solar system, turning the alien frontier from a distant curiosity into a tangible destination. Philosophically, the shadowed twin forces us to confront profound questions about our place in the universe. If life is found there, it would confirm that the processes leading to biology are not unique to Earth but are instead universal phenomena. Such a discovery would have sweeping implications, suggesting that life is likely common throughout the cosmos. Conversely, if the Crimson Sphere is barren despite its promising conditions, it would underscore the extraordinary rarity of Earth and the fragility of its ecosystems. Either outcome reshapes our understanding of existence and deepens our appreciation for the delicate balance of life. Culturally, the reddish haven has ignited a wave of creativity and introspection. It has inspired artists to imagine surreal landscapes bathed in dim red light, where alien life thrives in harmony with the unique rhythms of the planet. Writers have crafted stories of civilizations adapting to the eternal division of light and dark, while philosophers debate the ethical implications of exploring, or interfering with, potentially inhabited worlds. The Crimson Sanctuary serves as both a scientific challenge and a wellspring of human expression, uniting people across disciplines and borders. Ultimately, the Twilight Marvel is a testament to humanity's boundless curiosity. It reminds us that the universe is vast, filled with worlds waiting to be explored, each holding the potential to transform our understanding of life, evolution, and the cosmos. Whether it harbors life or stands as a silent, rocky witness to the passage of time, the alien beacon will forever inspire us to look to the stars and dream of what lies beyond.
Uranus is one of the most mysterious and fascinating planets in our solar system, a world that continues to puzzle scientists and inspire curiosity. It is the seventh planet from the Sun, orbiting at an average distance of about 2.87 billion kilometers, 1.78 billion miles. This icy giant stands out not only for its composition and unique features, but also for the challenges it poses to our understanding of planetary science. Discovered in 1781 by William Herschel, Uranus was the first planet found with the aid of a telescope. Unlike the 5 planets visible to the naked eye, Uranus marked the expansion of our cosmic horizons. Initially thought to be a star or comet, it was later confirmed as a planet, fundamentally changing how humanity viewed the solar system. One of the most striking characteristics of Uranus is its extreme axial tilt of 98 degrees. Unlike other planets, which spin more or less upright relative to their orbits, Uranus essentially rolls along its orbit, spinning on its side. This unique orientation creates extreme seasonal variations. Each pole experiences 42 Earth years of continuous sunlight, followed by 42 years of darkness. Scientists are still trying to fully understand the origin of this tilt, with the prevailing theory suggesting a massive collision with an Earth-sized object early in the planet's history. Uranus is classified as an ice giant, along with its sibling Neptune. While Jupiter and Saturn are dominated by hydrogen and helium, Uranus has a higher proportion of ices, such as water, ammonia, and methane in its interior. This methane is also responsible for the planet's pale blue color, as it absorbs red light and reflects blue. However, the planet's color is less vivid compared to Neptune's, possibly due to differences in atmospheric haze. Beneath Uranus' calm appearance lies a dynamic and turbulent atmosphere. The planet experiences supersonic winds reaching speeds of up to 900 kilometers per hour, 560 miles per hour. Its temperature drops to a frigid -224 degrees Celsius, -371 degrees Fahrenheit, making it the coldest planet in the solar system. Paradoxically, despite its icy nature, Uranus emits very little internal heat compared to other planets. This lack of heat flow is another mystery, as it suggests a unique thermal evolution. Uranus also has a complex magnetic field, which is significantly tilted from its rotational axis and offset from the planet's center. Unlike Earth's relatively symmetrical magnetic field, Uranus' magnetosphere is lopsided and highly dynamic, causing its magnetic poles to wander unpredictably. This field interacts with the solar wind to produce unusual auroras, which differ greatly from those observed on Earth and Jupiter. The planet is surrounded by a system of 13 faint rings and 27 known moons, all named after characters from Shakespeare and Alexander Pope's works. The rings are dark and narrow, composed of icy and rocky particles, possibly remnants of a shattered moon or comet. Among its moons, Titania and Oberon are the largest, with intriguing surfaces marked by canyons, impact craters, and possibly signs of subsurface activity. Exploration of Uranus has been limited to the flyby of NASA's Voyager 2 spacecraft in 1986. During its brief encounter, Voyager 2 provided a wealth of data, revealing details about the planet's atmosphere, rings, and moons. However, much remains unknown. Unlike Jupiter and Saturn, Uranus has not been revisited by any spacecraft, leaving it as one of the least studied planets in the solar system. Future missions to Uranus are a high priority for planetary scientists. Such missions could provide insights into the formation and evolution of ice giants, which are among the most common types of planets in our galaxy. Understanding Uranus could also shed light on exoplanets that share similar characteristics. Key goals include investigating its internal structure, atmospheric dynamics, magnetic field, and potential for subsurface oceans on its moons. Uranus challenges our understanding of planetary systems. Its unique characteristics, from its extreme tilt to its dynamic weather and mysterious interior, make it a compelling target for exploration. As technology advances and space agencies plan new missions, the icy giant may finally reveal its secrets, enriching our knowledge of not only the solar system but also the diversity of planets in the universe. Uranus, the seventh planet from the Sun, is one of the most intriguing and enigmatic worlds in our solar system. This ice giant, located approximately 2.87 billion kilometers, 178 billion miles, from the Sun, defies conventional planetary norms with its unique features, baffling scientists and captivating astronomers for centuries. Discovered in 1781 by the German-born British astronomer William Herschel, Uranus was the first planet identified with the aid of a telescope. Its discovery was revolutionary, expanding the known boundaries of the solar system and marking the beginning of modern planetary astronomy. Initially thought to be a comet or star, its true nature as a planet was confirmed through careful observation, altering humanity's understanding of the cosmos. One of Uranus's most striking features is its extreme axial tilt of approximately 98 degrees. Unlike any other planet in the solar system, Uranus spins almost entirely on its side. This means its poles face the Sun at different points in its orbit, leading to extreme and prolonged seasons. Each pole experiences 42 Earth years of continuous sunlight followed by 42 years of darkness, creating a climatic dynamic unlike anything on Earth. Scientists theorize that this tilt resulted from a colossal collision with an Earth-sized object during the early stages of the planet's formation. Uranus is classified as an ice giant, along with its neighbor Neptune. While Jupiter and Saturn are predominantly composed of hydrogen and helium, Uranus has a higher concentration of ices, which include water, ammonia, and methane. These substances exist under extreme pressure and temperatures within the planet's interior, contributing to its unique characteristics. The methane in its upper atmosphere absorbs red light, giving Uranus its pale blue color. However, its hue is less vibrant than Neptune's, possibly due to differences in atmospheric haze or chemical composition. The atmosphere of Uranus is a harsh, dynamic environment, with winds reaching speeds of up to 900 kilometers per hour, 560 miles per hour. It is the coldest planetary atmosphere in the solar system, with minimum temperatures plunging to -224 degrees Celsius, -371 degrees Fahrenheit. This frigid environment raises intriguing questions about the planet's thermal history, as Uranus emits surprisingly little internal heat compared to other giant planets. Another fascinating aspect of Uranus is its complex and asymmetric magnetic field. Unlike Earth, where the magnetic field is relatively aligned with the planet's rotational axis, Uranus's magnetic field is tilted by about 59 degrees and offset from its center. This lopsided and irregular field creates unique auroras and interacts with the solar wind in ways that remain poorly understood. Voyager 2, the only spacecraft to visit Uranus, revealed this peculiar magnetic environment during its 1986 flyby, leaving scientists eager for more detailed exploration. Uranus is surrounded by a faint ring system, consisting of 13 known rings primarily composed of dark particles. These rings are far less prominent than Saturn's, but they are fascinating in their own right, possibly formed from shattered moons or remnants of ancient collisions. Beyond its rings, Uranus has 27 known moons, all named after characters from Shakespearean plays and Alexander Pope's works. The largest moons, Titania, Oberon, Umbriel, Ariel, and Miranda, are icy worlds with intriguing geological features. including deep canyons, impact craters, and possibly even subsurface oceans. The moons of Uranus hold particular interest for astrobiologists. Some, like Miranda and Titania, may harbor subsurface oceans beneath their icy crusts. If confirmed, these oceans could contain the necessary conditions for life, such as liquid water and organic molecules. Understanding these environments is a key goal for future exploration, as they could shed light on the potential for habitability elsewhere in the solar system. Despite its scientific significance, Uranus remains one of the least studied planets in the solar system. Voyager 2's brief flyby provided valuable data, but it only scratched the surface of understanding this enigmatic world. Scientists advocate for a dedicated mission to Uranus, which could include an orbiter and atmospheric probe to investigate its composition, magnetic field, weather patterns, and moons in detail. Such a mission would also enhance our understanding of ice giants, which are among the most common types of planets discovered in other star systems. The study of Uranus is not just about understanding one planet. It is about gaining insights into the broader processes that govern planetary formation and evolution. Ice giants like Uranus challenge our models of planetary interiors, atmospheres, and magnetic fields. Moreover, their study could provide crucial context for interpreting observations of exoplanets with similar characteristics. In the future, missions to Uranus could revolutionize our knowledge of the outer solar system. An orbiter equipped with advanced instruments could map the planet's interior, analyze its atmosphere, and study its moons and rings in unprecedented detail. Such a mission would likely require innovative technologies, including nuclear-powered systems to sustain operations in the dim sunlight so far from the sun. Uranus embodies the mysteries of the outer solar system, challenging scientists to think beyond conventional models and explore the unknown. Its extreme tilt, frigid temperatures, complex magnetic field, and potential subsurface oceans make it a compelling target for future exploration. By unlocking the secrets of Uranus, humanity may uncover fundamental truths about the formation and evolution of planetary systems, both in our solar system and beyond. Exploration of Uranus also holds immense potential for understanding planetary systems beyond our own. Over the past 2 decades, thousands of exoplanets have been discovered orbiting other stars, and a significant fraction of these are ice giant analogs, planets similar in size and mass to Uranus and Neptune. Studying Uranus in detail can provide a critical reference point for interpreting data from these distant worlds, helping scientists determine their atmospheric composition, internal structures, and potential for hosting life. One of the most puzzling aspects of Uranus is its lack of significant heat emission. Unlike Jupiter, Saturn, and Neptune, which radiate more heat than they absorb from the sun, Uranus emits almost no detectable internal heat. This raises questions about the planet's formation and thermal evolution. Some theories suggest that Uranus experienced a cataclysmic impact during its early history, which not only caused its extreme axial tilt but also disrupted its internal heat distribution, effectively locking in its cold state. Understanding this anomaly could reveal new insights into the thermal dynamics of ice giants and their formation in the protoplanetary disk. The planet's atmosphere is another area of intense scientific curiosity. Beneath its calm blue exterior lies a complex system of storms, winds, and chemical reactions. Observations from Earth-based telescopes and the Hubble Space Telescope have detected bright spots and cloud systems that indicate dynamic weather patterns. These features suggest that, despite its low internal heat, Uranus has an active atmosphere driven by seasonal changes and possibly unknown processes occurring deep within the planet. Future missions equipped with high-resolution imaging and spectroscopy could provide a more detailed picture of these atmospheric phenomena. The rings and moons of Uranus are equally compelling targets for exploration. Unlike the dense, icy rings of Saturn, Uranus's rings are dark and sparse, likely composed of organic-rich materials. Their origin remains a mystery. Were they formed from ancient collisions, or are they remnants of the planet's early accretion process? Answering these questions could illuminate the processes that shaped the outer solar system. Uranus's moons, particularly Titania and Oberon, are prime candidates for detailed study. These moons are large enough to be considered dwarf planets if they orbited the Sun independently. Their surfaces, marked by craters, rifts, and other geological features, hint at a complex history of tectonic and possibly cryovolcanic activity. Subsurface oceans may exist on some of these moons, maintained by residual heat and the presence of antifreeze compounds like ammonia. Exploring these moons could provide invaluable clues about the conditions required for life and the potential for habitable environments on icy worlds. Moreover, Uranus's magnetic field adds another layer of complexity to its study. The tilted, offset nature of the field suggests that the planet's dynamo, a mechanism in its interior that generates the magnetic field, is fundamentally different from that of Earth or the gas giants. Understanding how this dynamo operates under the extreme pressures and compositions of Uranus's interior could expand our knowledge of planetary magnetism across a wide range of celestial bodies. The technology needed to explore Uranus poses its own set of challenges. Given its vast distance from the Sun, any spacecraft sent to Uranus must rely on nuclear-powered systems, such as radioisotope thermoelectric generators, RTGs, to function effectively in the dim light and frigid temperatures of the outer solar system. Communications delays of about 2.7 hours each way will also require advanced autonomous systems capable of conducting scientific operations without constant input from Earth. NASA and other space agencies are actively considering missions to Uranus, recognizing its scientific importance. A dedicated orbiter and atmospheric probe could revolutionize our understanding of ice giants, building on the limited but tantalizing data provided by Voyager 2. By diving into Uranus's atmosphere, the probe could directly measure its composition, temperature, and pressure, providing data that is impossible to obtain from Earth. Meanwhile, an orbiter could map the planet's magnetic field, study its rings and moons, and monitor its atmospheric activity over time. Exploring Uranus is about more than just unraveling the mysteries of a single planet. It is a journey to understand the processes that shape the diversity of planetary systems across the galaxy. Ice giants like Uranus are thought to form in specific regions of protoplanetary disks, migrating over time to their current positions. By studying Uranus, we can refine our models of how planets form, migrate, and interact within their systems. In the coming decades, as humanity ventures further into the cosmos, Uranus will likely play a central role in expanding our knowledge of planetary science. Its unique characteristics, extreme axial tilt, icy composition, unusual magnetic field, and dynamic moons, make it a natural laboratory for testing theories and uncovering new phenomena. By exploring this distant world, we not only deepen our understanding of our own solar system, but also gain a glimpse into the nature of countless other planetary systems that populate the universe. Uranus reminds us that even in our own cosmic backyard, there is so much left to discover. Each step toward its exploration brings us closer to answering fundamental questions about the origins and workings of planets, the potential for life beyond Earth, and the intricate dynamics of the cosmos itself. This icy giant, silent and distant, holds the keys to unlocking some of the most profound mysteries of existence. The potential for Uranus to unlock profound cosmic mysteries cannot be overstated. Despite its silent and distant presence, it holds answers to questions that extend far beyond our solar system. To truly grasp the significance of Uranus, we must delve deeper into what its exploration could reveal, not only about itself but about the nature of planetary systems and the broader universe. One of the most exciting prospects in studying Uranus lies in its connection to the field of comparative planetology. Ice giants like Uranus and Neptune occupy a middle ground between terrestrial planets, such as Earth and Mars, and the gas giants Jupiter and Saturn. This intermediate category bridges the gap in our understanding of planetary formation and evolution. By comparing Uranus with other planets, scientists can refine their theories about how planets develop over time, why their compositions vary, and how they interact with their environments. For instance, the atmospheric dynamics of Uranus are a puzzle waiting to be solved. Unlike Jupiter and Saturn, whose atmospheres are dominated by powerful storms and heat-driven convection, Uranus appears deceptively calm on the surface. However, its atmosphere is far from static. Infrared observations reveal complex cloud structures, likely composed of methane, ammonia, and water ice. These clouds, combined with supersonic winds and temperature inversions, hint at hidden processes driving atmospheric circulation. Understanding these dynamics could help scientists model atmospheres on distant exoplanets with similar compositions. Speaking of exoplanets, Uranus is an invaluable analog for studying planets beyond our solar system. Many of the exoplanets discovered to date fall into a category known as mini-Neptunes or sub-Neptunes, which are similar in size and composition to Uranus and Neptune. These planets are among the most common types in our galaxy, yet they remain poorly understood because we lack detailed observations of similar planets in our own system. By studying Uranus, we gain a Rosetta Stone for interpreting data on these distant worlds, helping us unlock their atmospheric compositions, internal structures, and potential for habitability. Another fascinating aspect of Uranus is its potential to host unique chemistry within its interior. The extreme pressures and temperatures inside Uranus may create exotic states of matter, such as superionic water, where hydrogen ions move freely within a lattice of oxygen atoms. This phase of water, which behaves like a conductor, could play a crucial role in generating Uranus's unusual magnetic field. Additionally, carbon within Uranus's interior might form diamonds, which could sink to the core in a diamond rain phenomenon. These processes are not only captivating in their own right, but also provide critical insights into how materials behave under extreme conditions. Uranus's moons add yet another layer of intrigue to its study. Each of its major moons, Titania, Oberon, Ariel, Umbriel, and Miranda, offers a unique geological story. Miranda, for instance, has one of the most unusual and varied surfaces in the solar system, featuring massive cliffs, ridges, and possibly evidence of cryovolcanism. Titania and Oberon, the largest moons, may harbor subsurface oceans, raising the possibility of environments capable of supporting microbial life. If confirmed, these moons could join the ranks of other ocean worlds in the solar system, such as Europa and Enceladus, as prime targets in the search for life. To explore Uranus effectively, future missions will need to leverage the latest advancements in technology and engineering. An orbiter equipped with instruments such as spectrometers, magnetometers, and imaging systems could conduct detailed surveys of the planet and its moons. A descent probe could directly sample the planet's atmosphere, providing data on its composition, temperature, and pressure gradients. Such a mission would represent a monumental leap in our understanding, comparable to the groundbreaking studies of Jupiter by the Juno spacecraft or Saturn by the Cassini-Huygens mission. The logistical challenges of reaching Uranus are significant but not insurmountable. Its vast distance from the Sun means that spacecraft must be equipped with power sources like radioisotope thermoelectric generators, RTGs, which can operate in low-light conditions. The journey itself, lasting 10 to 15 years depending on the launch window and trajectory, requires precise planning and execution. However, the scientific payoff would be immense, offering decades of data to analyze and interpret. Looking ahead, Uranus could also become a stepping stone for future exploration of the outer solar system. A mission to Uranus would serve as a testbed for technologies and techniques needed to explore even more distant worlds, such as Neptune and its largest moon, Triton. It could also pave the way for interstellar exploration by demonstrating our ability to operate spacecraft effectively at extreme distances from the Sun. Ultimately, Uranus reminds us of the boundless potential for discovery that lies within our own cosmic neighborhood. Every detail we uncover about this enigmatic planet, its atmosphere, interior, magnetic field, rings, and moons, adds another piece to the puzzle of how planets form, evolve, and interact. In studying Uranus, we not only deepen our understanding of the solar system, but also take steps toward answering some of the most profound questions about the universe. How common are planets like Earth? Could life exist elsewhere? What forces shape the cosmos we inhabit? The exploration of Uranus is not just an academic pursuit. It is a testament to humanity's unyielding curiosity and drive to explore the unknown. As we continue to push the boundaries of knowledge, Uranus stands as a beacon of possibility, inviting us to uncover its secrets and, in doing so, illuminate the mysteries of the universe. The journey to Uranus is not just a scientific endeavor but also a philosophical one. It represents our quest to understand our place in the cosmos and our connection to the processes that have shaped the solar system. Uranus, with its peculiarities and mysteries, offers a unique lens through which we can view the broader dynamics of planetary systems. One of the most profound questions that Uranus could help answer concerns the formation of ice giants. While the gas giants Jupiter and Saturn formed closer to the Sun and accumulated massive hydrogen and helium atmospheres, ice giants like Uranus and Neptune likely formed farther out, where water, ammonia, and methane could condense into solid ice. These volatile-rich planets might have formed their cores first, later capturing a thinner atmosphere of hydrogen and helium. But why did Uranus and Neptune stop growing, while Jupiter and Saturn continued to accumulate gas? And how did their migration to their current positions influence the development of the entire solar system? By studying Uranus's internal structure, scientists hope to uncover clues about this process. Current models suggest that the planet's interior is composed of a rocky core, surrounded by a thick layer of water, ammonia, and methane ices, and enveloped by a relatively thin hydrogen-helium atmosphere. However, there are significant uncertainties. For example, Uranus's lack of internal heat emission raises questions about its energy balance. Did an ancient collision disrupt its interior and scatter its heat outward, leaving it colder than expected? Understanding Uranus's thermal history is essential for piecing together the puzzle of its formation. Uranus's moons, too, hold keys to the planet's past. These natural satellites are not just passive companions. They interact dynamically with Uranus and its ring system. Tidal forces between the planet and its moons may heat their interiors, potentially sustaining subsurface oceans. Ariel, with its bright surface and apparent lack of craters, suggests recent geological activity, while Titania's large canyons hint at tectonic forces that reshaped its surface. Miranda, the smallest of the major moons, features enormous cliff faces and terrain so varied that it looks as though the moon was torn apart and reassembled. Each moon has a story to tell about the processes that shaped Uranus and its surroundings. The magnetic field of Uranus is another enigma. Unlike the relatively aligned magnetic fields of Earth and Jupiter, Uranus's field is tilted and off-center. This irregularity suggests that the dynamo generating the magnetic field is located in a shallow region of the planet's interior, possibly in its icy mantle. Such a configuration challenges traditional models of planetary magnetism and raises broader questions about how magnetic fields are generated in planets of different compositions and sizes. The potential for life on Uranus or its moons is an intriguing prospect, albeit a challenging one to evaluate. While the planet's extreme cold and lack of a solid surface make it inhospitable for life as we know it, its moons may tell a different story. Subsurface oceans, if present, could provide environments where life might exist. These oceans would be shielded from the harsh radiation of space and could contain the chemical ingredients necessary for life, driven by hydrothermal activity or tidal heating. Uranus also provides a unique opportunity to study planetary rings. Unlike Saturn's bright and expansive rings, the rings of Uranus are narrow, dark, and composed of material that absorbs more light than it reflects. Their origin is uncertain. Did they form from the debris of shattered moons, or are they remnants from the planet's formation? The ring's composition and dynamics could reveal new information about the evolution of the Uranian system and the forces that shape ring systems throughout the solar system. As space agencies plan future missions, Uranus emerges as a priority destination. NASA, for instance, has identified Uranus as a high-priority target for exploration in its decadal survey. A mission to Uranus could include an orbiter to study the planet, its rings and moons in detail, as well as an atmospheric probe to dive into its clouds and measure their composition and structure directly. This mission would not only answer questions about Uranus itself, but also pave the way for exploring other ice giants like Neptune, broadening our understanding of this class of planets. In the context of exoplanet research, Uranus serves as a critical benchmark. Many of the planets discovered around other stars fall into size categories similar to Uranus and Neptune, yet these mini-Neptunes remain poorly understood. By studying Uranus in detail, we gain insights that can be applied to these distant worlds. For example, understanding the atmospheric processes of Uranus could help interpret the spectra of exoplanets, revealing their atmospheric compositions and potential climates. Uranus also represents a step toward answering one of humanity's oldest questions. Are we alone in the universe? While the icy moons of Uranus are less well-studied than Europa or Enceladus, they could harbor conditions favorable to life. The discovery of even microbial life beneath the icy crust of a Uranian moon would have profound implications for our understanding of biology and its prevalence in the cosmos. In the grander scheme, Uranus is a reminder of how much there is left to explore. It challenges us to think beyond our familiar world, to push the boundaries of science and engineering, and to embrace the unknown. The mysteries of Uranus are not just puzzles to be solved. They are invitations to expand our horizons, to see the universe in new ways, and to deepen our appreciation for the complexity and beauty of the cosmos. As humanity looks toward the stars, Uranus stands as a gateway to the next great era of exploration. Its secrets, waiting to be uncovered, promise to enrich our understanding of the solar system and inspire generations to come. From its tilted axis to its icy moons and beyond, Uranus is a world that reminds us that the universe is full of wonders, just waiting for us to discover them. The exploration of Uranus is a story that stretches from our earliest understanding of the cosmos to the cutting-edge science of today, with the promise of even greater revelations in the future. To fully appreciate Uranus, we must consider not only what we know, but also the vast realms of the unknown it represents. Realms that invite curiosity, innovation, and a relentless drive to push the boundaries of our knowledge. The formation of Uranus is a mystery deeply tied to the broader evolution of the solar system. Current theories suggest that Uranus, like Neptune, formed in the colder outer regions of the protoplanetary disk, where ices could condense and coalesce into massive planetary cores. These cores, surrounded by lighter gases like hydrogen and helium, eventually became the ice giants we know today. But the exact sequence of events remains unclear. Why did Uranus and Neptune fail to grow as large as Jupiter and Saturn? Was their growth stunted by their position in the disk? Or did interactions with other forming planets scatter them outward, halting their development? Further complicating the picture is Uranus's axial tilt. The prevailing hypothesis is that a collision with a massive body, possibly as large as Earth, knocked Uranus onto its side during its early history. Such an event would have had profound effects on the planet's development, influencing everything from its rotation and internal heat distribution to the formation of its moons and rings. Investigating the scars of this ancient impact, whether through the dynamics of its satellites or the structure of its interior, could provide critical insights into the chaotic processes that shaped the early solar system. Uranus is a planet of extremes, a place where the familiar rules of planetary science seem to bend and break. Its tilted axis, which causes the planet to spin almost on its side, results in a bizarre seasonal cycle. Each pole experiences decades of continuous sunlight followed by decades of darkness, a phenomenon that drastically affects its atmosphere and weather patterns. This tilt is thought to be the result of a massive collision billions of years ago, yet the precise details of this event remain shrouded in mystery. What kind of object could have struck Uranus with enough force to tip it over? And how did such an event shape the planet's evolution over time? The planet's atmosphere, though serene in appearance, hides dynamic processes. Methane gives Uranus its pale blue color by absorbing red light, but beneath this calm exterior lies a chaotic world of storms and winds that reach speeds of up to 900 kilometers per hour. These winds, combined with the planet's extremely low temperatures, the coldest in the solar system, create an atmospheric system that defies easy explanation. Unlike Neptune, Uranus emits almost no internal heat, leaving scientists puzzled about the source of its atmospheric energy. Could the lack of heat be another clue to its tumultuous past, perhaps tied to the same event that tilted the planet? The magnetic field of Uranus is equally perplexing. Unlike Earth's relatively symmetrical magnetic field, Uranus's is wildly tilted and offset from the planet's center. This creates an asymmetrical magnetosphere that twists and bends as the planet rotates, generating unique auroras and interactions with the solar wind. Understanding how this magnetic field is generated could provide insights into the planet's interior, where extreme pressures and temperatures might produce exotic materials like superionic water, a phase of water that conducts electricity like a metal. Uranus is encircled by a system of narrow, dark rings that are both fascinating and mysterious. Unlike the bright and icy rings of Saturn, Uranus's rings are composed of darker material, possibly rich in organic compounds. Their origin is unknown. They may have formed from the remnants of a shattered moon or a captured comet. Studying these rings could reveal not only the history of the Uranian system but also broader truths about the formation and evolution of planetary ring systems throughout the solar system. Beyond the rings, Uranus boasts a collection of 27 moons, each with its own story to tell. Titania and Oberon, the largest moons, show evidence of past geological activity, such as tectonic rifts and impact craters. Miranda, with its dramatic cliffs and varied terrain, appears to have been torn apart and reassembled, suggesting a violent history. Some of these moons might even harbor subsurface oceans beneath their icy crusts, warmed by tidal forces or residual heat. If confirmed, these oceans could provide habitats for microbial life, making Uranus's moons key targets in the search for life beyond Earth. Despite its many mysteries, Uranus remains one of the least studied planets in the solar system. Voyager 2's flyby in 1986 provided the only close-up data we have, and much of what we know about the planet is still based on this brief encounter. However, new technologies and growing interest in ice giants have placed Uranus at the forefront of planetary science. Future missions to Uranus could include orbiters and atmospheric probes designed to study its atmosphere, interior, magnetic field, rings, and moons in unprecedented detail. Such missions would not only answer long-standing questions about Uranus but also provide critical data for understanding similar planets in other star systems. The importance of Uranus extends far beyond the solar system. Many of the exoplanets discovered in recent years are similar in size and composition to Uranus and Neptune, yet we know relatively little about these types of worlds. By studying Uranus in detail, we gain a window into the conditions and processes that shape ice giants, helping us interpret the data from distant exoplanets and refine our models of planetary formation and evolution. Uranus is a world of contradictions. A cold planet with dynamic winds, a tilted giant with a lopsided magnetic field, and a serene-looking orb that hides a turbulent past. Its exploration represents not just the next step in our understanding of the solar system but also a journey into the unknown. The secrets of Uranus hold the potential to redefine what we know about planets, not only in our own neighborhood but across the galaxy. Each question we answer about Uranus brings us closer to understanding the fundamental processes that govern the cosmos, reminding us that even the quietest, most distant corners of our solar system are filled with wonder. The journey to uncover Uranus's secrets is a testament to humanity's insatiable curiosity and drive to explore the unknown. While Uranus orbits quietly on the fringes of the solar system, its unique properties and mysteries make it a dynamic laboratory for answering some of the most profound questions in planetary science and beyond. Studying Uranus isn't just about understanding one planet, it's about understanding the broader context of how planets form and evolve. Ice giants like Uranus represent a middle ground between rocky terrestrial planets and massive gas giants, offering a critical missing piece in the puzzle of planetary diversity. By examining Uranus, we can better understand why the planets in our solar system are so different from one another and why planets in other systems seem to exhibit such an incredible variety of sizes, compositions, and orbital configurations. For example, many exoplanets discovered in recent years fall into categories known as mini-Neptunes or super-Earths, which share similarities with Uranus and Neptune in terms of size and possible composition. These planets are among the most common types found in the galaxy, yet they remain poorly understood. Uranus, as an accessible ice giant within our solar system, provides an invaluable analog for studying these distant worlds. Understanding its atmospheric composition, internal structure, and magnetic field could provide the key to deciphering data from exoplanetary systems. One of the most exciting prospects in Uranian exploration lies in its moons. Among the 27 known satellites of Uranus, the 5 largest, Titania, Oberon, Umbriel, Ariel, and Miranda, are especially intriguing. These moons are geologically diverse, with surfaces marked by canyons, craters, and evidence of past tectonic activity. Some even show signs of cryovolcanism, where icy materials erupt instead of molten rock, reshaping their surfaces over time. Titania, the largest moon, is particularly interesting because it may harbor a subsurface ocean beneath its icy crust. If such an ocean exists, it could potentially support microbial life, shielded from harsh radiation and sustained by chemical energy from the moon's interior. Similarly, Ariel, with its relatively smooth surface and bright features, might hold clues to recent geological activity that could also indicate the presence of subsurface liquid water. Miranda, the smallest of the major moons, is perhaps the most visually striking. Its surface is a patchwork of immense cliffs, ridges, and unique formations that appear to be the result of multiple episodes of tectonic and cryovolcanic activity. The origin of Miranda's bizarre terrain remains a mystery, but its study could reveal much about the forces shaping icy moons across the solar system. Exploring these moons could provide critical insights into the potential for life on icy worlds. As scientists increasingly consider subsurface oceans as prime locations for habitability, Uranus's moons offer compelling targets for future missions. They may even rival Europa or Enceladus, moons of Jupiter and Saturn, as candidates for astrobiological studies. Sending a mission to Uranus presents significant engineering and technological challenges. Its vast distance from Earth means that a spacecraft must travel for 10 to 15 years to reach the planet, depending on the trajectory and available propulsion systems. Once there, the spacecraft would need to operate in extremely cold temperatures and communicate across billions of kilometers, with round-trip signals taking nearly 6 hours. Powering such a mission requires advanced systems like radioisotope thermoelectric generators, RTGs, which can generate electricity from the heat produced by radioactive decay. These generators have been successfully used in missions to deep space destinations such as Saturn and Pluto. Additionally, instruments designed to withstand the frigid environment of Uranus would need to be lightweight, robust, and capable of operating autonomously due to the time delay in communications. A future Uranus mission would likely consist of an orbiter and an atmospheric probe. The orbiter would conduct long-term studies of the planet, its moons, rings, and magnetic field, while the probe would descend into Uranus's atmosphere, directly sampling its composition and structure. Together, these components would provide an unprecedented level of detail about the planet and its system. The exploration of Uranus is not just about solving planetary mysteries. It's about pushing the boundaries of human knowledge. By studying this distant world, we gain a deeper understanding of the processes that govern the solar system, from planetary formation to magnetic field generation and the dynamics of icy environments. Uranus also serves as a stepping stone for future exploration of even more distant worlds. Lessons learned from a Uranus mission could inform future missions to Neptune and its largest moon, Triton, a world with an active surface and retrograde orbit that suggests it may be a captured Kuiper belt object. Beyond Neptune, Uranus could serve as a gateway to understanding the vast, unexplored regions of the outer solar system, including the Kuiper belt and Oort cloud. In the context of humanity's broader exploration goals, Uranus represents a vital frontier. As we develop the technologies and capabilities to study distant planets, we also prepare for the challenges of interstellar exploration. The knowledge gained from Uranus could one day guide us as we venture beyond the solar system, seeking to understand the countless planetary systems scattered across the galaxy. Uranus reminds us that even in the quietest and most distant corners of our solar system, there are stories waiting to be uncovered. Its tilted axis, icy moons, and dynamic atmosphere are just the surface of the mysteries it holds. Each step toward exploring Uranus brings us closer to understanding not only this enigmatic planet, but also the processes that have shaped the universe itself. As humanity continues to look outward, Uranus stands as a beacon of possibility. Its exploration promises to deepen our knowledge of planetary science, inspire future generations of scientists and engineers, and remind us of the boundless potential of human curiosity. In the silent, icy depths of Uranus lies the promise of discovery, one that could redefine our understanding of the cosmos and our place within it. Uranus is not just another distant planet in the solar system. It is a cosmic enigma waiting to ignite our imagination and challenge everything we think we know about planetary science. It's a world of extremes, contradictions, and mysteries that dares us to explore and uncover its secrets. Imagine standing on one of its icy moons, looking up at the pale blue giant looming in the sky, surrounded by faint rings that whisper of ancient collisions and cosmic drama. This is the allure of Uranus, a planet that is both serene and chaotic, familiar yet utterly alien. Unlike any other planet, Uranus rotates on its side, as if the universe itself decided to defy the norm. This extreme tilt isn't just a curiosity. It transforms the planet into a world of wild seasons where one pole basks in sunlight for decades, while the other endures an equally long, frigid night. Picture this. A single day on Uranus lasts 17 Earth hours, but a year spans 84 Earth years, making its seasons not just long but otherworldly. What would it feel like to experience 42 years of continuous sunlight followed by 42 years of unbroken darkness? This tilt creates conditions we have never seen on Earth or any other planet, making Uranus a natural laboratory for studying extreme planetary climates. Beneath its calm, pastel blue appearance, Uranus's atmosphere is anything but serene. Here, winds howl at supersonic speeds, reaching up to 900 kilometers per hour, 560 miles per hour. These gales sweep across a world that is colder than any other in the solar system, with temperatures plunging to a bone-chilling -224 degrees Celsius, -371 degrees Fahrenheit. How does a planet that emits almost no internal heat sustain such ferocious winds? Scientists are baffled, and the answers could reshape our understanding of atmospheric physics. Uranus's rings, though faint and understated compared to Saturn's, are no less fascinating. They are narrow, dark, and composed of materials so ancient and enigmatic that their very existence poses questions about the planet's violent past. Did they form from the debris of a shattered moon? Are they remnants of the planet's chaotic formation billions of years ago? These rings are like whispers from a forgotten era, waiting for us to decode their secrets. And what could be more thrilling than the possibility of discovering something entirely unexpected? Something no one has imagined. The moons of Uranus are worlds unto themselves, each one unique, each one a mystery. Titania, with its vast canyons and ancient surface, may hide a subsurface ocean teeming with possibilities. Uranus is a planet that defies expectations. Its tilted axis, spinning almost completely on its side, creates a world where the rules we know simply don't apply. Imagine a planet where sunlight bathes one pole for 42 Earth years, while the other plunges into unbroken darkness. This extreme tilt isn't just a feature. It's a signature of a dramatic history. Scientists believe Uranus may have been struck by a massive object in its early life, a collision so catastrophic that it forever changed its orientation. What kind of chaos must have unfolded to leave such a mark? Exploring Uranus is a chance to unravel this cosmic mystery and understand the forces that shaped it. The atmosphere of Uranus is another enigma. At first glance, its pale blue hue seems calm and inviting, but beneath this serene exterior lies a world of ferocious winds and dynamic weather. Winds on Uranus reach speeds of 900 kilometers per hour, sweeping across an atmosphere colder than anywhere else in the solar system, with temperatures plummeting to -224 degrees Celsius. Despite this frigid environment, the planet shows occasional bursts of activity, with bright clouds and storms appearing suddenly. How can such extremes coexist? What powers these mysterious atmospheric events on a planet that emits almost no internal heat? These are questions that only direct exploration can answer. Surrounding Uranus is a delicate system of rings, starkly different from the bright, icy bands of Saturn. These rings are narrow, dark, and composed of material that absorbs more light than it reflects. They are ancient, silent witnesses to Uranus's history, possibly born from the debris of shattered moons or leftover fragments from the planet's formation. Yet, their composition, origin, and evolution remain unknown. What secrets lie in these thin, shadowy bands? Could they hold clues to the violent past of the Uranian system or even broader insights into how ring systems form across the solar system? Beyond the rings lies a collection of moons, each one unique and full of mysteries. The 5 largest moons, Titania, Oberon, Umbriel, Ariel, and Miranda, are icy worlds that may harbor hidden oceans beneath their surfaces. Titania, the largest, shows signs of past geological activity, with massive canyons and potential cryovolcanic features. Could its interior still be warm enough to sustain a liquid ocean? Miranda, on the other hand, is a world of extremes. Its surface is a patchwork of cliffs, ridges, and valleys so bizarre it looks like it has been ripped apart and reassembled. What kind of forces created this chaotic landscape? These moons are not just icy rocks. They are potential treasure troves of information about the conditions that may support life in the most unexpected places. Even the magnetic field of Uranus is an anomaly. Unlike Earth's field, which is relatively aligned with its rotational axis, Uranus's magnetic field is tilted at a wild angle and offset from the planet's center. This creates a magnetosphere that twists and warps unpredictably as the planet spins. Studying this field could unlock new understanding about how magnetic fields are generated in ice giants and what role they play in protecting planets and moons from cosmic radiation. Despite its incredible potential for discovery, Uranus remains one of the least explored planets in the solar system. Voyager 2's brief flyby in 1986 gave us a tantalizing glimpse, but it only scratched the surface of what we need to know. Imagine sending a mission designed specifically for Uranus. A spacecraft equipped with advanced instruments to map its atmosphere, study its rings, and explore its moons up close. An atmospheric probe could descend through its thick clouds, directly sampling the gases and revealing the secrets of its composition. An orbiter could spend years unraveling the mysteries of its magnetic field, tracking storms, and capturing stunning images of its moons and rings. Studying Uranus isn't just about understanding one planet. Ice giants like Uranus and Neptune are among the most common types of planets found in other star systems. By exploring Uranus, we gain a crucial reference point for understanding these distant worlds. How do they form? What are their atmospheres made of? Could they host moons with conditions suitable for life? Every discovery we make on Uranus brings us closer to answering these questions on a galactic scale. Uranus challenges us to think beyond what we know. It's a world of contradictions, a cold planet with violent winds, a tilted giant with a lopsided magnetic field, and a serene-looking orb that hides a turbulent past. Its exploration is not just a scientific endeavor. It's an invitation to push the boundaries of human curiosity and innovation. In the icy depths of Uranus lie answers to some of the most profound questions about the solar system and the universe. Every step we take toward exploring it is a step closer to understanding the cosmos and our place within it. Uranus is a silent giant, patiently waiting on the edge of our solar system, holding secrets that could transform our understanding of planets, moons, and even the formation of life itself. Its mysteries are not just puzzles to be solved. They are gateways to a deeper connection with the cosmos, a reminder that even the most distant and quiet corners of the universe are alive with stories waiting to be told. Imagine a mission to Uranus. The spacecraft launches from Earth, carrying humanity's dreams of discovery on a journey spanning more than a decade. As it approaches the ice giant, the first close-up images arrive. The pale blue sphere dominates the screen, its faint rings glowing softly against the blackness of space. The spacecraft begins its work, mapping the planet's magnetic field, analyzing its atmosphere, and capturing the first high-resolution images of its moons. Each transmission from Uranus is like a letter from the frontier, bringing news of worlds we've never truly seen before. The atmospheric probe descends into the clouds of Uranus, a slow and deliberate plunge into the unknown. Instruments detect layers of methane, hydrogen, and helium, revealing subtle variations in temperature and pressure that hint at the planet's complex weather systems. Perhaps it detects unexpected chemical signatures, compounds that challenge our models and hint at processes we've never encountered. The probe's descent is brief, but its discoveries will resonate for decades, shaping our understanding of ice giants and the atmospheres of planets around distant stars. Meanwhile, the orbiter turns its attention to Uranus's moons. High above Titania, it captures images of vast canyons and shimmering icy plains, searching for clues about a potential subsurface ocean. It moves on to Miranda, where towering cliffs cast long shadows across a patchwork surface, a testament to the moon's violent history. Data streams back to Earth, sparking debates and inspiring theories. Could there be hydrothermal activity beneath these moons? Could life exist, hidden beneath layers of ice and rock? The possibilities are staggering. As the spacecraft studies Uranus's rings, it reveals details too fine to see from Earth. The rings, dark and mysterious, may hold answers about the planet's early history. Perhaps they were born from the remnants of a moon torn apart by gravitational forces. Or maybe they're the leftovers of a colossal impact billions of years ago, the same event that tipped Uranus onto its side. Each fragment of ring material tells a story, each orbit a chapter in the history of the Uranian system. This mission isn't just about data, it's about rekindling